Ebin sir joined, sir. Ebin sir already joined. Celsi?
Yes, sir.
Yeah. Ma'am? Panjame ma'am, shall we start? Anand sir?
Yeah.
Yeah, okay.
Please
Okay.
proceed, sir.
Thank you. Yes, okay, sir. Celsi, please.
Okay, sir. A very good morning to all the esteemed delegates, eminent faculties, and dear participants. It is indeed a privilege to welcome you all to this 5-day FDP cum workshop on contemporary image processing and security applications, organized by the Department of CSE Cybersecurity and EC in association with CyberLabs, as per Cybersecurity Lab and ELIX Club in IIIT Kottayam. Today, we will delve into two crucial areas of technology that are shaping our world, that is, contemporary image processing and cybersecurity applications. These fields are not only fascinating, but also essential in today's digital landscape. Our program aims to equip you with latest insights and tools to integrate these topics into your curriculum effectively. We will
Maybe
explore the
from her
latest
side.
advancements, best practices, and practical applications to enhance your teaching and research capabilities. Prayer is an invocation of heart, a calling forth of divine energies to be manifested in one's life. Time spent in prayer refreshes, renews, and strengthens our mind and soul. Let's start with a prayer song. എങ്ങുമെങ്ങും നിറയും വെളിച്ചമേ എൻ മനസ്സിൽ കുടിയിരിക്കണമേ എന്റെ പാദം ഇടരാതിരിക്കുവാൻ എന്നും എന്നിൽ ദയ ചൊരിയണമേ പൂവിലൂറുന്ന പുഞ്ചിരി നീയല്ലോ പുസ്തകം തരും ജ്ഞാനവും നീയല്ലോ പുല്ലുമാടവും പൂമണിമേടയും തുല്യമായി തൊഴും ശക്തിയും നീയല്ലോ നല്ല ചിന്തയായി എൻ്റെ മനസ്സിലും നല്ല ഭാഷയായി നാവിൻ്റെ തുമ്പിലും നല്ല ചെയ്തിയാൽ എൻ്റെ കരത്തിലും നന്മയാം നീ കടന്നിരിക്കണമേ നല്ല ചെയ്തിയാൽ എൻ്റെ കരത്തിലും നന്മയാം നീ കടന്നിരിക്കണമേ. A warm welcome is the first sign of hospitality. I would like to invite Dr. E. Silambarasan Sir, Assistant Professor, Department of Cybersecurity, to deliver the welcome address.
Thank you, Celsi. Good morning to one and all. On behalf of IIIT Kottayam, I extend a heartily welcome to all of you to our 5-day FDP cum workshop on contemporary image processing and cybersecurity application. I extend a warm welcome to our director, sir, Dr. Rajivi Daraskar, whose vision and guidance have been instrumental in the inspection of FDP cum workshop. Your unwavering support for academic endeavors is truly commendable, and we are grateful for your presence here. In his absence, here, I welcome you, sir. I extend a warm welcome to our beloved registrar, sir, Dr. Radhakrishnan. His invaluable contribution and support in ensuring the FTP cum workshop succeed. In his absence, here, I welcome you, sir. I extend a warm welcome to our HOD ma'am, Dr. Panchami, and Department of CSE Cybersecurity, and Dr. A. Anand, sir, HOD, Department of ECE. They are the backbone of this FTP cum workshop. They are taking care of each and every step of this event. Next, I extend a warm welcome to all our resource persons who have gracefully accepted to be the part of this event. I believe that their sessions will bring to extremely beneficial. I extend a warm welcome to our academic dean, our chief guest today, Dr. Abi Daniel, sir, and HODs of CSE, FICs, and faculty members. I welcome all club members like Cybersecurity Club and ELIX Club and research groups, CyberLabs, and Aspire. Last but not least, I extend my warm welcome to all external and internal participants for gracing this occasion with your presence. Your enthusiasm and eagerness to learn are truly inspiring, and I hope this workshop will be a rewarding experience for you all. We are looking forward to work with you in the future also. Once again, I welcome to all uh, this program to enriching the journey of learning, discovery, and growth. Thank you, one and all. Over to Celsi.
Thank you, sir, for your cordial words. It's my pleasure to invite Dr. Ebin Deniraj, Associate Dean, Academic Affairs, to deliver the inaugural address.
Yeah, I hope I'm audible.
Yes, sir.
Yeah, thanks. Thank you, Chelsea. So it's really a pleasure to see the 5-day workshop on quantum image processing and security related area. So this topic is very relevant, and especially with usually we say with more data, you have more responsibility. And obviously, this topic is the need of the hour, I would say. And as far as IIIT Kottayam is concerned, we always make sure that we are kind of aligned and resonant with the industry standards. And also, we act as a bridge between academia and industry. So it is really good to see that 50 participants are there, and also that from various backgrounds. And IIIT Kottayam, even though it was established hardly 8 years back, within a short span of time, we are one of the leading IIITs in the country. And the reason for that, there are many reasons. Out of that, I would say one primary reason is that the good industry connect we have. And these sorts of faculty development programs, some workshops are definitely a testimony of like how we do things and also how we align with the industry. And the as a faculty, I would say like if you're working in any IT or IT allied areas, it is an ever changing and ever evolving domain. So if we are not ready to learn new things, obviously we'll be out of the race. We'll not be able to kind of face the challenges, because especially with ChatGPT and all the AI related tools, unless and until we update ourselves, it is very difficult to kind of teach to students as well as kind of update ourselves with the latest technology. So in this context, I definitely congratulate all the participants who have registered for this workshop. And also I appreciate your eagerness to learn these technology, especially the combination of image processing and security. Of course, it is even from a traditional perspective, there has been works being done in these two domains, but maybe in the last 4 or 5 years, the importance of these two domains have increased very, very significantly. So I'm sure the next 5 days will be definitely very fruitful for the participants. And also, I want to congratulate all the organizers, especially the Department of Cybersecurity and the Department of Electronics and Communication. And definitely, I'm sure that these 5 days will be fruitful and useful for you from a career perspective. And also the organizers, especially Dr. Silambaresan and Dr. Santosh. I also want to congratulate them for taking the effort and kind of keeping it in this way. And I wish you all the very best, and thank you so much.
Thank you, sir, for your insightful words. It's my pleasure to invite Dr. Panchami V, Head of the Department Cybersecurity, to deliver the felicitation address.
Thank you, Chelsea. Good morning. First of all, let me congratulate Dr. Silambaresan and Dr. Santosh, the coordinators and participants of this 5-day FDP cum workshop on contemporary image processing and cybersecurity applications. So this workshop is a unique program, as this is the first time we are conducting a workshop in collaboration with EC department. And we, while we are designing the schedule, we have to we make sure about that. We have to start from the very basics of image processing with a hands-on session on Python. And after that, discussing about the various algorithms, architectures of image and the video signal processing. Then moving on to the medical image analysis. After that, we move on to the cryptographic primitives of image image security. Then we also discuss about the image forensic, malware detection, and we will end the schedule with the digital image security. So we have covered almost all the areas of the image processing and its application of the cybersecurity. See, when we speak about the domain of cybersecurity on image processing system, or this image processing system plays an important role to analyze or dictate the threats and malwares in image files, or even in video files. Furthermore, these kinds of systems or these kinds of protocols you can also use to extract the hidden information from the images, and that will be a great use in the domain of image forensic. Hence, I strongly believe that this workshop will contribute a lot to upgrade your skill sets. So once again, on behalf of CIPCSA Cybersecurity Department of IIT Kottayam, I wish all the participants and resource person a very comfortable and a fruitful session ahead. I assure you that there will be a wholehearted support and involvement from our department, Cybersecurity of IIT Kottayam. Thank you all.
Thank you, ma'am, for your encouraging words. I invite Dr. Anand A, HOD, EC Department, IIT Kottayam, to deliver the felicitation address.
So, good morning and a warm welcome to all. So, it gives me immense pleasure to deliver the felicitation address for this wonderful 5-day FDP cum workshop on contemporary image processing and cybersecurity applications organized by the Department of ECE and the Department of CSE Cybersecurity in association with Aspire, AI-powered signal and image processing research group and CyberLabs research group, along with our students club, ELIX and cybersecurity club. first and foremost, I would like to appreciate the organizers of this workshop, Dr. Silambarasan sir and Dr. Santosh Kumar sir, because they both were from two different departments of our institute, and they have come together to offer a workshop which is the need of the hour. Okay, and also this is the first workshop that is having a collaboration between the faculty members of cyber security and ECE. So I wish them all good for successful completion of this workshop, and also take this workshop forward in various collaborative measures. Okay, and also I would like to cite that this is the first workshop that is offered at our institute during the summer, even though we have so many workshops in various domains like ECE and AI and data science, CSE and cyber security, computational science and humanities. So many workshops are in pipeline, but they were the luckiest people, or otherwise I have to say, like they were the nice people who has initiated things in the right directions. So I wish them all again for this. So in addition to this, in our institute, we also offer certain programs during summer, like internships for UG, PG and PhD scholars, to bridge the gap for between the industry and academia, where our faculties of various departments will sit work with the students to gain knowledge in different domains. So that is one more thing that may feel attractive. And right from the day of beginning, I was very well known how Silambarasan sir and Santosh Kumar sir have taken efforts to bring this event in a night shape. Because if you look at the schedule for this workshop, you can see they were covering each and every aspect of signal processing, how signal or other image processing, how this image processing augments with cyber security applications, and how it will be useful for research aspect and various other aspects. So I really appreciate their effort. In addition to this, I wish all the participants who are attending this workshop to have a great learning experience through this workshop. And I recommend all the participants to stay connected with the organizers and various other expert speakers throughout the globe. You can see the browser, we have speakers from our institute and also throughout the globe. Stay connected with them, collaborate with them, so that there will be a nice outcome from our land, that's India. Okay, so that we'll be feel happy or proud about it at later part. Okay, so with this few words, I would like to thank the organizers and also all the participants to gain a significant amount of knowledge in these two domains of image processing, how it is aligned with cyber security. So thank you once again.
Thank you, sir, for your cordial words. On behalf of everyone present here today, I would like to invite Dr. Santosh Kumar, Assistant Professor, Department of EC, to deliver the vote of thanks.
Thank you, sir. Esteemed Director, respected Registrar, dear Associate Dean, dear Head of the Departments, esteemed faculty members, and dear participants, a very good morning to all of you. With a heart full of gratitude, I address you as we conclude the inaugural session of our workshop on contemporary image processing and cyber security applications. This event would not have been possible without the support and participation of each one of you. We extend our sincere thanks to our visionary director, Dr. Raju V. Daraskar sir, in his absence. We are extremely grateful to you, sir. We extend our sincere thanks to our registrar, Dr. M. Radhakrishnan sir, in his absence. His support is invaluable to us, and we are extremely grateful to you, sir. We extend our sincere thanks to our Associate Dean, Dr. Ebin Deniraj sir, for inaugurating this session, this FDP cum workshop. I would like to thank all the distinguished speakers for their enlightening talks on cutting-edge technologies in image processing and cyber security. Your expertise has set the tone for an exciting and informative workshop. I would also like to thank our head of the department, CSC Cyber Security, Dr. Panchami Madam, and head of the department, Electronics and Communication Engineering, Dr. Anand Sir, for their moral support, guidance, mentorship in organizing this FDP cum workshop. To all the participants who have joined us from various institutions and backgrounds, thank you for your active participation. Your enthusiasm and curiosity drive the spirit of learning. I must also acknowledge the effort of our IT support team to ensure the smooth running of this event. Your hard work and dedication have not gone unnoticed. We, as we proceed with the workshop, let us carry forward the spirit of collaboration and learning that has been fostered here today. Together, we can explore new frontiers in image processing and cybersecurity, make a positive impact in our respective fields. Once again, thanks to everyone who has contributed to the success of this inaugural session. I look forward to the rest of the workshop with great anticipation. Thank you.
Thank you, sir, for your cordial words. I would like to take this opportunity to extend my gratitude to everyone present here. Thank you for gracing this inaugural event with your presence. Now I request everyone to turn on the camera to take a photo.
SLC done.
Thank you all. The session will resume at 11.
Welcome back to technical session. Uh, Ladies and gentlemen, it is my honor to introduce Dr. P. Sumati ma'am. Uh, Dr. P. Sumati has been working as a professor in the Department of Electrical Engineering, IIT Roorkee, Uttarakhand since August 2020. She is also presently associated with Henan University of Technology, China, as an adjunct research professor since May 2024. She served as the visiting associate professor in the Department of Telecommunication and ICT, School of Engineering and Technology, AIT Bangkok, from August 2018 to December 2018, as a part of a faculty secondment program sponsored by MHRD. He received a BE in EEE from SRM College of Engineering, Chennai, and ME in Control and Instrumentation from College of Engineering, Guindy, Anna University, Chennai. She received her PhD in Electrical Engineering from IIT Madras. She has published 30 research articles in reputed journals such as IEEE and IET. She has published 27 articles in international conference. She has guided 4 PhD scholars and 27 master students. She is a senior member of IEEE and a reviewer for IEEE transaction papers. She has completed a few projects funded by DST, DRDO, and BRC in control and signal processing algorithms and artificial intelligence. Please join me in welcoming Dr. P. Sumati ma'am. Over to ma'am.
Thank you, Dr. Santosh, for this introduction. And it's a privilege, a great privilege to be with you all today to give the talk on perception module for ADAS. So I understand this is related to the image processing and cybersecurity applications. But I think, could you please sharing the screen? Shall I share
Yes,
the
ma'am,
screen?
you can
Yeah.
share the screen, ma'am.
Yeah.
You have the permissions.
Screen is visible?
Yes, ma'am. Yes, yes.
Thank you. So I think our audience, I think audience are from different background. I just would like to touch upon this perception module related to the ADAS, Advanced Driver Assistance Systems, for this topic, for this talk actually. As Santosh introduced, I am associated with the IIT Roorkee since 2011. Joined as an assistant professor and then associate and became professor in August 2020. Also, I'm working in the research group of instrumentation and signal processing. So graduated from my PhD is from IIT Madras, and there the research work was designing the ultrasonic range measurement system. That was the topic which I had worked on, and we have developed a range measurement system using the ultrasonic sensors. And based on this, and then I started working on these instrumentation systems, basically using 1D signals, that is signal processing concepts, and applying them, mostly implementing those algorithms in the field programmable gate arrays. Now then recently switched on to the 2D signals as well, image processing, doing the image processing and extending this 1D signal processing concepts to the 2D. And most of them we focus on the ADAS. So the ADAS is the booming area, you know, the people are working. Still, we want to do the design of this very ADAS system, the instrumentation used for the ADAS systems. That's what we focus. For today's topic, I would like to go, I have arranged my topic like the presentation in this manner. So ADAS, first I would like to give you the what is ADAS, Advanced Driver Assistance Systems. I don't know how many of you are familiar with, and then I would like to give. Yeah. Next would be the taxonomy of the ADAS. So what are these classifications? What are the terminologies used in this ADAS, and what are the sensor types applicable to it? And then further continuing with that, ADAS deployable sensors. So if you want to make a perception module for ADAS, then really you need a more and more types of, because you need the 360-degree view of the car. So in that the vehicle, so it requires many sensors. So what are those sensors, and what is the purpose of those sensors, and really how these are deployed? So this is the third part which I want to discuss on. And then moving on to the vision-based ADAS. So specifically focusing on, there are ADAS has many like LiDAR, other sensors. Our focus is vision-based, that is only the camera based. So if you capture an image through a camera, then what would be what are the ways in which we can develop the systems? Basically, for ADAS, what we are doing, that would be focused on in the next part of this 2D kernels and edge detection, and how for the road images, and using that edge detection and how the lane detection is performed, how the object tracking is performed, and the vehicle tracking is done. So then little bit of AI I want to give, even that is the deep learning based algorithms also we work on, and I would like to touch upon at the end for the deep learning concepts. So when we take about this ADAS, the global status report of the WHO says, like in 2009, it was 1.2 million people die every year on world roads accident. So 20 and 50 million suffer non-fatal injuries because of that. And in 2015 report, it is 1.25. It is still increased. And 2023 report says that even 1.19 million, there is this estimate is little reduced. The 5%, there is a drop to the 1.25 million deaths in 10 and 25 reports. So the concern of the fatality, fatal injuries, and then reducing those road accidents. So, and ADAS, every car manufacturer are now deploying their ADAS systems. So, and in different ways and means, how the even though it is growing, I mean, it is being adapted in the different cars, and it is a long way to go to fully autonomous system, so our autonomous vehicle in the car. But there are by knowing the statistics, actually from the WHO, a global status report. Now, so what are the safety systems? ADAS is majorly focusing on the safety systems. So the first, there are two categories of the safety systems we need to think of. One is to protect the occupants within the vehicle first, when you are driving, when you are traveling, or when you are driving. So the one who is sitting inside the vehicle is one, for their safety is one, which is to be protected. The occupants' safety is one major concern, and the second one is prevent the injuries. Suppose some accident happens, how the people outside the vehicle. So inside a vehicle and outside the vehicle, how these safety systems can be helpful, are built in the ADAS and introduced in the ADAS. So it depends on that. It's categorized into two types of safety systems. If you come the two types, basically, again, if we among this inside the vehicle and the outside the vehicle, there are these two types also has the passive and active safety systems. So passive safety systems, it protect the vehicle occupants from injury after a crash. So if there is some accident happened after the crash, so what are the safety systems will be helpful? Okay, that is coming under the first category, which is called the passive. So those are seat belts, airbags, and padded dashboards. So these are coming under the passive one. If you take the active one, active safety systems are they prevent crash from happening. So altogether, like how we can assist the driver, or there comes the importance of ADAS. So lane keeping assist. So keep the vehicle driving in a lane. Automatic braking. If something has happened, the speed is suppose it is over speeding, and tell the driver that reduce the speed. And adaptive cruise control, that is knowing the preceding vehicle speed and accordingly adjust the speed of the host vehicle. So these are the preventive mechanisms, which is part of the ADAS. But the OEM, that these manufacturers, automotive society, they concentrate on active along with the passive. So passive is anyway, it's already well established techniques are available. But in the active case, still there are things. The research is still going on with that. So lane keeping assist and automatic braking, and these are a few examples of the adaptive cruise. So please stop me if you have any questions, audience. Hope I think you're able to follow till now.
Yes, madam.
Yeah, sure, thank you. In the taxonomy of ADAS, so how this is classified? Actually, what are the sensors used mainly? How are they classified? So there are at least 4 categories. So we have this first one, which is called the vision based or vision sensors. Okay, and the next one is the LiDAR, light detection and ranging, and third one is the radar, Fourth one is ultrasonic. These four are mainly used in ADAS. Apart from that, we have others also, like PMD, and then that is photonic mixer device. So this is inertial measurement units, and GPS. These are coming under other categories, which is not our focus. But still, there are other sensors also used. Those are categorized as others. But in vision, the predominant or the primary focus is the vision based. So in the vision based, we have the three classes of sensors are the cameras used in the vision based systems. One is monocular, and the second one is the stereotype and infrared. So these three types of cameras are being used in ADAS systems. And if you check the radar one, it is short to medium range, and then another one is a long range radar. So there are two types of, again, radar systems. So the next one. So if we look at the knowing the sensors which are used, now we can move on to this. I think this diagram is visible to you. Now, if we check the different types of these sensors, what we had classified are mainly used in the car in this fashion. So you can see the full view of to get the full view of how these things are used. So ultrasonic, this is the you can see the yellow color, which is used in the park assist. So for very short distances, so ultrasonic sensors are used. Those are the areas you can see, the park assist. And the short or medium range, you can see the purple color. So where it gives these sensor radar are used in cross traffic alert, blind spot detection, and also the rear collision warning. So to develop these systems, okay, so this data is useful, the radar data is useful, the short to medium range. So I am going to discuss each and every one with the distance, how much is the distance it is going to cover in the following slides. And then we'll move on to the real development of it. So next one is the camera, where you can see the camera which helps in the mirror, the side mirrors, which gives the surrounding view total. You can also see the blue color around it, and at the back side you can even have the surround view, the camera surround view. Here can have this the camera, and other thing is the lane keep assist or traffic sign recognition also comes under this vision one. So majorly if you see, this camera is helpful in getting the more information and designing the safety systems. So the next one here is the LiDAR. The LiDAR used in automatic braking, pedestrian detection, collision avoidance. It has a certain range. Again, we'll go check with the range which is used. And adaptive cruise control is a long range radar. So it has to check with it has to estimate the speed of the preceding vehicle and adjust the speed of the host vehicle according to the that speed, that is host vehicle, preceding vehicle speed. The host vehicle speed is adjusted. So the adaptive cruise control helps in that. So these long range radar, long and short range radar, LiDAR, camera, and ultrasonic, so can get the whole help in developing the whole perception module. So you can get the 360-degree view of the whole complete view of the outside the car, so that the safety systems, the ADAS systems can be developed. So the next we come on to this. So knowing this sensing modality. So the different types of sensors. First is a camera, LiDAR, radar, ultrasonic sensor, and these are giving the wider or different variety of the ADAS solutions. So the challenges involved in this are mainly design of ADAS and implementation itself. So if we have, how do we implement? Whether can we go for this? If you make the model of AI, then where will you keep your system in the? So how big your system is, and if you go for the chip level module, then the design, the implementation is a real challenge to put everything inside the chip. So and then operation of ADAS, it's remain to be overcome. So these are the challenges, really, design, implementation, and the operation. So how some of these challenges, mainly of this energy consumption, when you put the module inside a car, so that really the how do you operate that energy consumption, and reducing latency, the response latency, how quickly you can react to any of the condition, or the decision making needs to be faster, and adapting the changing to weather conditions. So weather condition is a real challenge. Maybe those are classified as adverse conditions. So I'll also have one slide. What are the types of adverse conditions you can have in this? So snowy and rainy, and you are now nothing is visible in before. It is foggy. The winter is so severe if you come to this. So north. So in that case, it is very difficult to drive. So those are the weather conditions are mainly the challenges, and the security, of course, is another challenge. So from that, first we take the vision sensor, that is cameras. So the cameras, as we told, there are two. I can see the camera design, camera types. It's a monocular, stereo, and infrared sensor cameras. So from that, go to the take this one. So vision sensors, in that the vision based ADAS, mainly my focus is that how this camera information is very much useful in this ADAS. So here one or more cameras are used to capture the images, because when you want to capture the front side of the car, and so you need one camera, and the rear side there is at least another camera is required. So and an embedded system to process, detect and detect what are the objects in that, or analyze them, and tracking the vehicle before. So these can be done with the only cameras. So in high-end ADAS, if we take them, the cameras are used to monitor this both inside and outside of the vehicle, so that the speed inside, and then, for example, the speed, okay, so at the outside also. When the cameras capture the image has these informations, the color, the contrast, and the texture. So which is a unique advantage of this sense, to have this sensor. So when you have, with respect to the color, you can get some information. For example, the traffic sign, if it is red, stop sign is red. So if I recognize, my algorithm could pick those pixels only, the red color pixels, then it is very much useful. And if you see the traffic on the road scenarios, so there are writings on the road, or the traffic symbols written on that. So the pedestrian crossings, so white and black zebra crossings. So these are related to the color. So the color information which is contained in the image, mainly the RGB. images. So we can also talk about the thermal images and so on. But basically, I take it here is RGB images. So the contrast of the image and the texture of the image. So these are giving the certain information. So what is this monocular and stereo cameras? There are two types of cameras mainly, and IR also in another type. So monocular and stereo cameras, in which the monocular camera have only one lens, so the one which normally that we have. So it captures, the focal length, and the object which is in front of the lens is focused to the screen. So that is a simple one lens camera. So the applications of this one lens camera, even if you have one lens, the monocular camera, the images captured using that is you can detect the obstacles, pedestrians, lanes, and the traffic signs. These are all required in the ADAS system. So for taking the decision or to assist the driver, to develop a system to assist the driver. Also, it is only one camera, or the monocular camera image, can be used for monitoring the person inside the vehicle also. So and he can detect the face and eye detection. So these are also can be a person who is sitting inside the vehicle. So with the camera, you can detect the face expression or the eye movement, okay, of the driver. So based on that, he's sleepy or he's drowsy, those things, the driver can be alerted with that information. So the head pose analysis, when he's fell asleep suddenly, so you can have a jerk movement. So we worked on that. So head pose analysis is another area in which you can monitor the driver. So these are even with an image, which is a camera which is placed inside the vehicle, can give you this information of the vehicle, face, eye detection, and then post analysis. So what is the problem with the monocular camera? So the camera, which is a normal one, only one lens, it doesn't have the depth information, meaning so the human eye, which can see, there is the human eye has a distance between the two eyes, so it can focus on a particular object, and it can see what distance this object is. Okay, suppose this is the object. Okay, so we can perceive that our vision. So to check this depth, that is what distance. So it is near to the eyes, or it's a faraway object, or whatever the distance, approximate distance. So you can perceive the distance information or the depth information, whereas these monocular cameras lacks in giving this information. Okay, so we can't get the depth information of the when you capture an image with the monocular camera. So so what we do to get the depth information in that case, so the stereo cameras are useful. So the stereo cameras are mainly the having two or more lenses. So it is having two or more lenses. So with image sensor, each lens has the image sensor anyway. So as in the monocular also, it is separated by a certain distance. So it has this is having a certain distance in the stereo camera, and that is called the stereo base. So stereo base is nothing but, as I told you, if you have two cameras, this is the baseline, okay, between the two cameras. So you can fix a monocular camera, two monocular camera, one is on the left and another is on the right. So the distance between it, so they capture the image from this camera and the other one also, same object, and you can correlate those two images and get the depth information as well. That is possible. That's another challenging area which you can work also. This is with the monocular camera. can we get the depth information? Can we estimate the depth information? So this is another. So, but stereo cameras directly give this depth information. So it has a stereo base, the two lenses, for example, 2 or more lenses it has. So these are useful in 3D information. So extracting the 3D information are using the two-dimensional images, one or more two-dimensional images, and matching this stereo pairs and images of left and right sensors. So as I told, the stereo camera will be combining the two. It will have two lenses, so left and right. So the relative depth of the scene can be estimated using that. So this the depth information also, it is depending on the length of the base. If you have the longer base, and you can have the object which are see here, this is proportional to the object distance also. So if you have the longer and longer one can be, if it is shorter, and you can have the shorter length, shorter scenes. So what are the applications of this stereo camera? So it is mainly useful for extracting the depth information. So ADAS systems are nowadays accompanying this, even we kept with the stereo cameras as well. So this is mainly useful in traffic sign recognition, like the traffic scenes, the symbols are the signs which are on the road to be recognized, whether to move right or left or right, and then what is especially the speed limits and the stop sign. So those are coming under the traffic sign detection. So the lanes, especially in the lanes, if you have the two sides, suppose it's a single lane or a double lane. So, the stereo cameras can give us helpful to detect these lanes, pedestrians on the lane or crossing the lane, and the obstacles on the scene. Okay, so it can give the distance estimation. Basically, why we need this stereo one? We want to know the distance of the preceding vehicle, or we want to know the distance of the pedestrian who is walking on the or crossing the road. Okay, so for distance information of the object which is before the host vehicle, the stereo cameras are very much helpful to extract that information. So which is giving greater accuracy compared to the monochrome cameras. And the one is the distance. When we say the distance information using the stereo camera, it can be only 30 meters. Okay, so I think this is sufficient range to make a decision, any decision on it. So 30 meter is quite a good number. So 30 meter distance, within that, this can you estimate the distance. And where these stereo cameras are located, actually it's not on the dashboard, or it's not outside the vehicle. It is located inside the vehicle. You can see that it is located inside the vehicle, behind the rear view mirror. So you know the mirror placed inside the vehicle, and this is placed behind the rear view mirror, and it is angled slightly downwards to see the depth. Okay, facing the road. So this is the way in which it is installed in the inside the vehicle, the stereo cameras. When we go to the next category of this vision sensor, so monocular camera, you can capture the image before the eye, and the next one is the stereo cameras, which is giving the another dimension to the image what you capture. And IR cameras, again, this is giving the different perspective of the perspective before the vehicle. So one is this active IR cameras, and the next one is the passive IR cameras. So the two categories, how does it help us? So the active IR cameras, it has a light source in itself. Okay, so that's why it is called active. It has it can emit this IR between the range of 750 to 1400 nanometer. So it's the wavelength. and which is built in the vehicle to illuminate the scene. That means it can illuminate the scene, so that which obviously this nanometer range we cannot see, the human eye cannot see. So it can illuminate the scene, and then the normal camera, that is a digital camera sensor, which capture the image. So that is the reflected from the IR. So the reflected light is received by the digital camera. In this case, that's an IR active one. So in case of passive, so the passive doesn't have the light source. Okay, so that is the difference between this active and the passive one. So I'll get to this passive case. So the passive case here is where every pixel of the IR can be considered temperature sensor. So that can capture only the thermal radiation emitted by any material. So if it passes the what is the variation in the temperature? Okay, so that is sensed by these IR cameras. So we have so it is a passive IR camera, but it doesn't have any light source. That's why it is not it doesn't have any IR light source in the case of active IR. So night vision solutions, so especially low light conditions. Okay, that is very challenging when it is completely dark. Okay, so we are also working on those images. So can you identify a pedestrian when it is completely dark? Okay, so in that case, these IR cameras are very much useful. Either it is active IR or the passive one. Okay, so video, especially it is used in the low light conditions. So passive IR, it doesn't have any special illumination of the scene. So that is about the IR. So you have the third category, which is useful in the night vision. Okay, so mainly taking the night vision camera, nighttime details. So this can be used. So the next category of the sensor. So apart from the camera side vision sensors, like the monocular, stereo, and the IR cameras, so which is adding another dimension to the information which you get to model which you use it for the ADAS development systems. So LiDAR is actually the which is used for always the object detection. Anyway, it is used. This information is primarily used for this object detection. So how does it work? Most of you have a laser beam which is impinged on the object, and it is received by a sensor. Okay, so it can be either the same or it can be another sensor. So in that case, how much is the light time traveled? Okay, so that gives the distance of the object. So if you take even the ultrasonic sensor, the same principle is used. So you just ultrasonic sensors, ultrasonic wave is impinged on an object, and either you can have an ultrasonic receiver, separately one more receiver, or you can use this transmitter itself as a sensor. So the light travel and then bounce back, or the reflected from the object is analyzed or processed for the time information it has traveled. So the same way, this laser beam impinged at an object and then measuring the time taken for the light to bounce back to the sensor. So just to calculate this is a common, very very common method to find the distance of an object. So it can achieve high resolution 3D images. These LiDAR images are longer ranges than camera range. That is why. So what is the difference between this LiDAR and the vision one? So how much distance it can cover? Okay, so it will be useful for the automatic braking, object detection. Okay, collision avoidance. These are, you have to take a decision very quickly, suppose imagine the scene of collision avoidance. Okay, so and then automatic braking. You need to further the distance. It needs to be it needs to take the decision that the driver or the autonomous vehicle should be taking the decision. So in that case, it is the lidars are actually for 60 meters. Okay. So whereas in the case of IR and the monochlor, these things can cover 30-meter range. Okay, the camera generally. So here is the 60-meter range for the lidar, and which is this system, the lidar system is heavy, and the source it's expensive, also bulky in size. It is very much useful. The lidars light detection and ranging is used in rain, foggy condition of the image. It is capturing the or getting the information is very useful, and using the lidar. So this is expensive, and that part is taken care these days by emerging solid state lidars. That's another area which is going on. So the next one I would like to give you this radar. So the radar systems, the next category. So 30-meter range, 60-meter range, and then see the remaining one for the radar. So if you go to the radar ranges here, so if you see radar, how much it needs to be covered. So okay, so the long range and the short range radar, there are long range and short range as well. Okay, so you can see the ranges where it is used. So it emits microwave. Here is the source. Source is a microwave, okay, and estimate the speed of the distance of an object by measuring the frequency reflected from it. So I think this principle is, if we have a continuous, it is also used in the continuous mode of ultrasonics. So this will be transmitted, and the reflected one, the reflected wave from this will have a phase shift, okay, from the object. So when it is transmitted and it is received from that, so if this is the transmitted wave and this is the received wave, so the transmitted and received wave have the phase shift. So the phase shift information is directly proportional to the distance of the object and the time taken. So the frequency, if the object is moving, and this phase shift will be changing with respect to time, so it becomes a frequency modulation, and the frequency of the transmitted wave started modulating, so it would change that is reflected in the received wave. So the moving object velocity can be even estimated using the frequency, what is tracking the frequency of the received wave. So this is called the Doppler effect, so which is very much useful. And even if you say the object is vibrating, or what is the speed at which it is vibrating, and if assuming that it is a sinusoidal vibration, or so the Doppler effect can be, there are algorithms to extract this Doppler effect. If it is if the object is moving in a linear fashion, so the reflected wave can also be having the linear change in the frequency. So that can be estimated using this. So why we use the radar here. So longer wavelength, so microwave or longer wavelength, the frequency is high, and so it can travel much farther. And then because optical light, which is used in the LiDAR, here is the longer distance can be covered using this. What is the distance here? So we have two types of, even the three types we can say. Short and medium are together called, but if you strictly classify them, the short range is only 0.2 to 30 meter, and whereas medium range is of 30 to 80 meters, long range 80 to 200 meters. So from zero to 200 meters, these sensors can give the information to the development of these ADAS safety systems. So the cameras, and then the LiDAR, and the radar. So radar itself is classified to this short range, medium range, and then long range radars. So in the case of the radar is not affected by foggy and rainy weather conditions, so it is inexpensive also. So next. Applications mainly I have seen the cross traffic alerts. So we have seen in the cross traffic alerts, blind spot detection. It is very much essential in the ADAS. Okay, so these are used in the short and medium range radars. So where these systems are located? Okay, so the rider one. So these systems are often located at corners of the vehicle. Okay, so this corner and the another corner. And adaptive cruise control is long range radar application. So I have showed you in that image where we have seen the long range case. This is a long range one. Sorry. So how this improvement is required in case of cost reduction and power of the system in radar. So those are the two challenges for the radar information to be implemented or used in the ADAS. Ultrasonics, it's very cheap. Ultrasonic sensors, you get 300 rupees even. So these are used, the sound waves are used, mainly used that one is a 40 kilohertz sensor. It's very cheap sensor we have, but that is may not be useful, but you need a good sensor in the ADAS systems. This uses the sound waves to measure the distance object. The principle, I think it as I told you, is mainly the transmitter and there is a receiver, or you can have the transmitter and the receiver one sensor can be used as both also as well. So in the country there are two modes of operation. The continuous wave can be transmitted, and the received wave is checked for the phase shift if the object is stationary. If object is moving, then it is checked for the frequency, which is the received wave frequency, so that this velocity can be obtained or the distance can be obtained from this. Or it can be a pulse kind of thing. You can send the pulse in a regular interval. This will be the transmitting pulses, and the received pulse, whatever the received pulse are correlated with this. Do the correlation of the transmitted pulse and the received pulse, and then the distance is estimated using the correlation. So better to have a transmitter and receiver separately. When you have only one sensor as transmitter or the receiver, in that case we need to take care of the pulses which is not be missed. So it should be received before receiving. You should not send the second pulse or the next pulse. So those things needs to be taken care when we use this sensors. So very close to the object, like a rear view, park assist. So in the park assist, it is very much useful, the ultrasonic sensors. You can see there the ultrasonic sensors, the park assist, the yellow shaded ones are the main focus. The ones which are the objects which are close to the vehicle. So automatic parking and then parallel parking assist. These are the applications in which the ultrasonic sensors are used. So these sensors are located under front and rear bumper of the vehicle. It is almost all the vehicles have these recent days has this ultrasonic sensors, front and rear bumper way of the vehicles. So those are the categories we have discussed. So this vision, and then the LiDAR, radar, and the ultrasonic sensors, the four types. So for the other things which are coming, if you can use the GPS information to locate this vehicle or navigate that vehicle on the road, that is one. And another inertial measurement units also available. Those units can also be used. And the photonic mixer devices, those are even the array of smart sensors, okay, which can give the optical sensing. So these sensors also are part of the ADAS these days. These are other categories. So PM, it supports the pixel-wise correlation of the objects. So which can give the information like lateral resolution, faster imaging, and the depth information, all of them. So these are the one which I have covered so far are the sensing modalities mainly used in the ADAS. So if we focus on the vision only, okay. So coming back to the vision sensors and vision based ADAS. So how the vision data flow is useful. That is very easy for us to take that going for the radar information and the LiDAR information. Instead of those things, I mean, fixing one camera on the car, that would be more easier than doing the rest of the things. So in the vision-based ADAS, so these are the steps of the data flow model of this. Is an image. First is the image acquisition, capturing the image, okay. And then do the pre-processing if anything required, and the segmentation to extract the features are in the roadside road scenarios. So you need to separate the lane, and you need to separate the background, and you need to separate the sky and the tree, those things. So that can be done using the segmentation, and then the object detection and tracking, and get the depth information and use it for the systems and control. So we'll see one by one. These are how they are being done. So this is process of capturing a frame from a video. So recording the video is one, or you take only one image, one frame of the image is the acquisition. So you have the recorded video, suppose. So this acquisition is taking the frames from the video. So each individually you need to take out the frames. So anyway, processing is not fully done with the video. We have to process it with the frames. So the video needs to be changed to the frames. And then these frames are often represented with the pixels. So the image consists of the pixel information, and this pixel the data which has RGB red, green, and blue sets of pixels. These are the three channels which gives the information about the image scene which is captured. So the frame rates generally available are the 5 frames per second to 60 frames per second. So depending on the application. So whether we need to go for the 5 frames per second or 60 frames per second. Okay. So how do we decide on that? So the applications involve vehicle proximity, okay, need higher frame rates due to rapid change in distance for cars on the road. So if you are capturing the scene of the closer proximity, in that case, so if the preceding vehicle is very quick, the scene can change very quickly. So in that you need to have the frame rate higher. Okay, so it goes on the higher side, that is 60 frames per second. Whereas in the other category called the traffic sign detection, this is not going to change. The traffic sign should be stagnant or stationary in one place. Okay, so your car only will be moving. So that scene can be used with low frame rates. So 5 fps to 60 fps. So when we analyze it for traffic signs, so then it's farther away. I mean, it is far away. These signs to be detected in that case, the frame rate can be less. Whereas the closer scenes needs to be captured at the higher frame rates. so that the scene activity changes very quickly, because to capture those changes, instantaneous ones. So in that case, you need more frame rates. What are all the pre-processing? Because based on the, we have to prepare the image for the computer vision algorithms, like denoising. First, need to remove the noise, as we do in the 1D case, 1D signals. Color enhancement. So that is another one. Color space conversion, RGB to the other colors, which is required. And then image stabilization, if something is hazy or so, they need to be processed. So color space conversion, one case is the convert RGB to hue saturation, okay, and HSV. So value, hue saturation and value. So just separate color from the intensity. So first RGB can be made into hue saturation and value, and those hue saturation and value can be used for the processing. So the hue channel is often used to separate adverse effects like the shadows. So you can see where it is, it is depending on the application. To make these shadows, you want to know the information of the shadows. The shadows are very much useful. Uneven lighting, over and under exposure images. Suppose a car which is moving, you have captured the image. So, okay, so the shadow is also due to the light or sunlight. You have the shadow along with that. Okay, so when you want to detect this object, so the object detector wrongly identifies this as a whole image along with the shadow. The shadow need not be an object. Okay, so shadow needs to be removed in that case. So the hue channel, if you process the hue channel for it, then you can remove this shadow. So in the object detection, you can only focus on the object. The bounding box can be drawn only for the object, not the object and the shadow. So this is one. So that is a few pre-processing cases. And the segmentation, the process of separating the features from what are the features we are looking for, only the lane, partition them into recognizable objects, which as road or sky or what is in the frame, or the trees. The background is not required. When I am focusing on only the lane detection part, then my background is not a matter. So if I want to know where these two lanes are suppose converging, so two lanes, 2 points I am drawing from the lane, suppose, for the sum of the purpose. So the vanishing point, where this scene is getting ending. Okay, so finding the vanishing point of the scene. Okay, so in that case, your background is important. So where background of the image is important, or where you don't require the background. Okay, so it depends on the application. So the segmentation is helpful. The focus, you need to identify different features from the scene. So thresholding techniques are useful always to filter one class of the pixels from the other class. That is, road has some pixel and sky has some other pixel. So if you simply use the thresholding, it can be helpful. So even the variable threshold, adaptive thresholding, those things will also be helpful. So as I told you, the color information is helpful to detect the stop sign. That is only looking for, in the case of stop sign, only looking for red color, and then remove rest of the pixels. It is not of importance in that case. So binary images is often used as a mask in the image processing, the segmentation process. So detecting the lines or so you can create the binary images for masking, and then to find the area of interest of the original image. That is also another process which can be used. Coming to the next data flow, or once you have the image captured and you got the frame, and then pre-processing, and after the segmentation after pre-processing to the segmentation, and then comes to the object detection. So it's very, very, very important in the ADAS. So classifying the object depends on whether the object is first of all moving or stationary. There are two classes even. Suppose object ahead is a vehicle or a sign or a pedestrian or a cyclist. There are many classes we can have in the detection. So there are in the object detection, the supreme technique we can say is the machine learning technique. Okay, you can get as many information as possible through the data sets, the many images, and then differentiate them as vehicles and objects, the cyclist and the pedestrian, and so on. Use the machine learning algorithms. The classifiers object detection method is also the cascade classifiers. It is at the end having the classifier, which is used to have the face detection of the face detection event in this case. So CNN is also used for this classification. So in that CNN, you know, maybe it has an input layer and the multiple hidden layers and an output layer. So the hidden layers mainly have the concept of the convolution layer and the pooling layer. It's a max pool layer. And then they are used for the feature extraction, and then the fully connected layer for the classification. This is a very basic in the CNN. Can be used for this object detection. Also, the CNN frameworks, darknet, also is useful. In the object tracking, especially object detection these are CNN frameworks are quite good. And for tracking, whenever there is a tracking case, then we need to depend on the Kalman filter based object trackings are very much useful. Here also it is very much essential to in the vision based the depth information. Okay, so how to estimate the distance of the object if the camera with respect to the camera frame. Okay, so there are two methods as we told. One is stereo camera, so we use it, and another one is the monochrome camera. So monochrome cameras, you take the information and try to analyze it, because in the stereo camera you get, as I told you, you can directly get the depth information because it has at least two lenses. Whereas in the monocular, you have the only one lens, and the image is captured, and then it relies on these methods like optical flow, calibration, least square techniques are much useful in these cases to obtain the depth information. So systems and control is deciding based on all this based on these processes like image acquisition, and then pre-processing, and then segmentation and object detection, and then the tracking on all of this. What is the confidence level of the object detection? So these decisions are made in the systems and control. A major challenge would be the false detection. So how much we can reduce the false detection, how to increase the confidence level. So this is one challenge. And training the data with correct and content, always data is the source that for the accuracy, you can say. So how much data you have, you get the more accuracy, more classifications with higher accuracy is possible. So training the data with as much as possible data. So one example here, the stop sign detection. You can see the road scenario in which a binary stop sign. This is the binary stop sign and stop sign classification, the right side, using the optical character recognition. So it's simply checking the character recognition technique. Stop, STOP, you have to check for it in the image. So see the confidence levels achieved. So one is farther away, and so middle one is middle one has we could recognize better also. So this is for this 0.92 confidence level, and here 0.8897 confidence level. So it depends on the image. So in this way, optical character recognition is used in the road sign detection. So pedestrian detection is also it's a big challenge in the case. So there are various classifiers used for it, detecting and using the classifiers. More often, one classifier used for detecting the people and varying the orientation, configuration. If the which pedestrian, suppose pedestrian can walk, so and the orientation may also be different when the pedestrian. So these things should be considered using basically the CNNs are used, deep learning networks. For the vehicle detection is a major focus in the ADAS, in the vision-based ADAS, basically, but mainly in ADAS and in the vision-based ADAS, the pedestrian and vehicle, these are the two major objects, major things to be detected. So how this vehicle is detected? Okay, so it's like if a scene which has a tire. So the algorithm can contain this type of information, like if it has tire, if it has a brake light, so, and if it has a license plate. So allow the detection of the object to indicate where that is the car is there. So if whether it is a car or not, what are the cases can be considered? What are the things, the signs can be considered here if there is a tire? Okay, and then the braking light, and then also the license plate detection. Those are helpful in finding the car or detecting the vehicle. So these are the features used. These are the features to distinguish the vehicle from the object. So if you have all these features, then say that is a vehicle and it's not an object. So objects can be signs, roads, and other objects on the image. So for object detection, for example, in this image, have the lane detection, and the vehicle detected, okay, and the traffic sign detected. Okay, so these are so three detections possible: lane, vehicle, and the traffic sign. Okay, so this is information can be used in the ADAS. So CNN darknet and YOLO are mainly used in the real-time detections. Orientation of the vehicle also a matter. If you have the image with the various orientations, okay, so different set of features needs to be considered in this case. So often classifiers use vehicles means we have used at least 7 classes, I think. So cars, trucks, and with many orientations. Okay, so we have to put all the vehicles in the classifiers as much as possible. Traffic sign detection. It supports, these days it is used for this. So speed limit. So determining the speed limit, suppose 40 or 20, it is to alert the driver if he exceeds the 40 speed limit. So the traffic sign which is showing the speed limit can be detected and inform the driver that you are exceeding the speed limit. So color thresholds are used in this using the optical character recognition methods for the traffic sign detection and location. So the next one, vehicle, pedestrian, sign, traffic sign, and then the next one is the lane detection. So in the lane detection, it's a very important detection in the ADAS, where why the lane need to be detected, okay, in the ADAS. So to keep the vehicle within the lane. So the vehicle navigation needs to be within the lane. So it should not cross, the vehicle should not cross, or the driver should not cross the lane. That is, in that case, it is to be, there is a threshold where you can give the driver a warning called a lane departure. Your vehicle is deviating from the lane. Okay. So that is, those are the to issue that warning, so lane departure warning, are to keep the vehicle within the lane. We need to detect the lane. Okay. So there are quite a good challenges in the lane detection. So there in the roads you may not see the lane lines at all. Okay, and there may be a curved lanes. So straight lines can be detected. If there is a curved line, then that detection would be another challenge. So hardest features, so those lane lines are different colors, faded, and sometimes not even present in that. So those are the scenarios in which these lane lines are to be hardest. These are the features which needs to be accommodated in the training data set, so that the lane lines can be detected if you use an ML algorithms. So basically, before getting into the lane detection, the canny edge detector is used for first getting the edges of the image. Okay, so the image captured by the monochrome camera, which is processed for the edge detection. So canny is a very popular edge detector. So using that edge detection, once the edges are detected, and then a half transform, which is used to find the lines between the edges. So I think you might be familiar with the half transform. So that this half transform can give the lines between the two points. Okay, so that this is confirmed to be a lane. CNNs are also popular for this. CNNs can be used, and the other one in this collision avoidance, which is to be incorporated for the automatic braking and the ADAS. So it is done with the combining these features like object tracking, vehicle detection, and distance estimation. So the collision or predicting the collision can be done with object detect, track, vehicle detection, and distance estimation. These three things will be helpful to identify predict the collision. Predict the collision. If it exceeds certain limit, then we can issue warning that the collision, so that the speed can be reduced, or the steering can be put in another direction. So these warnings can be given to the driver. So based on this, all the levels of driving information, the Automotive Society of Engineers, so safety automotive societies, have the these kind of classifications, or the levels of autonomous driving cars. There is, if the level of the automation is 0, there is no automation at all. A driver drives the vehicle, the normal one, that is zero level, and the one giving the driver assistance, there is a human driver in level 1 automation. Level 2 automation also, there is a human driver. And the partial automation 1 and 2, the differences I'll give you. And the third one is the system where the conditional automation, and fourth one is high automation, and fifth level of autonomous driving systems are the fully automatic. So no driver involved in that. So these are the the levels of automation, we can say. So the 0, 1, there is no the handling. ADAS is no driver is. The driver is driving, and there is no assistant to the driver in the handling the steering or acceleration and the deacceleration and so on. So manually driven by the driver, that is 0 level. The first level has the the driver is assisted with either steering or acceleration deacceleration. So these two cases, any one of this will be assisted for the level 1 automation. Level 2 automation, both steering acceleration and deacceleration under certain conditions, certain environments only, the human driver is assisted given the input. Both that is the level 2. So in 0, 1, 2, there is a driver, and the fourth one mainly that is what 0 to 2, the driver monitors the driving environment. So the system is not monitoring the driving environment, whereas the other cases like 3, 4, 5, level 3, 4, 5, the environment is monitored by the ADAS systems. Okay. So third is the Tesla ones. So the 3 levels, it has the level 3 systems. The driver is intervened when needed. That's all. By the okay, so the driver intervenes. Driver intervenes when needed. That means our systems takes care of everything. That is the top level. The modern vehicles are having this 3. And the fourth one operate wider range of environments. That is multiple safety systems and a wider range of the environment comes under the fourth one. And fifth one is fully autonomous. That is automation is autonomous driving. So completely it is a lot more to achieve in this direction. 5. So should I continue, Santosh?
Yes, ma'am.
Any questions? Or shall I continue?
Yes, madam, you can continue.
Yeah. Okay. So I just want to so far I have given the overview, or what are the.
Yes, madam.
Yeah.
Yes, ma'am.
I'm continuing. Yeah, I'm continuing.
Yes, madam. Yes, madam.
So the whole infrastructure, the architecture of the ADAS system has four major verticals. One is the sensors. Another one is that lane detection, traffic sign, traffic lights, object detection, object tracking. That is another vertical. This is the perception module which we are to support. So if you are developing a perception module, then we need to focus on lane detection, traffic light detection, traffic sign, object detection, object tracking. And another third vertical is the planning. In the system architecture, we have the route planning, prediction, behavior planning, trajectory planning. Those are another category of this. And then control comes into the navigation, full navigation of the vehicle. That is the fourth vertical. So for the perception module, we need all this sensor data, camera, radar, LiDAR, and others also. This is the overall system architecture. So what we do in the first of all, taking the lane detection part. That is in this case, the first one. We take the lane detection, the first category of it. So the work which we are doing, I just would like to share the work what we are doing for another some 10-15 minutes or so. So here we take the first part is the lane detection. In the lane detection, which is very much essential for the perception module development. So the lane detection is done with the edge detectors. So the edge detectors, there are the CANI is proven to be one, but there are two types of edge detector. If you have gone through the image processing techniques, that gradient methods and the Laplacian kernels. So the first derivative and second derivatives are observed, and the threshold is fixed for the first derivatives, and then in the second derivative there is a crossing. Zero crossing is identified. So these are the two types of edge detectors you have. So what we find when I was going through these signal processing algorithms like the sliding DFT one, which I'm working on for a longer time. So in that we find that this STFT we can use it for the DFT. Of course, the sliding DFT is a recursive form of DFT computation. So when I focus on in a 1D signal, which is of having the harmonics. Okay, so that is a fundamental and second harmonic plus third harmonic and fourth harmonic, whatever the harmonics we have. So this signal, when it is passed to the DFT here, and I can tune this DFT as a filter, sliding DFT, to extract only the fundamental, only DC, fundamental, second harmonic, third harmonic, and so on. Instantaneous waveforms can be obtained from this. So with this background, I was just thinking this image is also a case of sines and cosines, sum of sines and cosines in both the directions. So why don't we use this? And the edges are also of one frequency. Okay, so if we have the, you can say high frequency, the transition is very quick in the intensity, so you can say it's in a high frequency region. So edge in the image is also a frequency. So why don't we use this DFT, sliding DFT, as an edge detector? So that's the idea which has come to my mind. So we started working on it, and that is the equation is a 2D DFT here. So this DFT, how do we get in the fundamentals DC and second harmonic and third harmonic in case of 1D? By changing the bin index. So bin index k equal to 1. So from the DFT equation, 0, 1, 2, 3 to n minus 1. If this tuned to 0, this can give me DC. And if it is 1 fundamental and 2, it can give me the second harmonic and so on. So similarly, in 2D, this will be a 2 bin indices, that K1 and K2. Okay, so this is K1 and K2. This is a frequency domain information, which I get from the pixel values, okay, in the images. So if I vary this K1 and K2, different combination. Suppose N is 3, N1 and N2 are 3 by 3. Okay, so then I can have these K1 varying from 0, 1, 2 and K2 varying from 0, 1, 2. So K1, 0 and K2, 0 is going to give me one certain information from the image, and 0, 1, if I fix it, it can give another information. 1, 0 can give me the other information. So combinations of it, 2, 0 and 0, 2 can also extract to the certain information from the image. So this is the idea which we had used and developed a kernel like an edge one. So for this is giving the 3 by 3 image, the sliding DFT equation. So with the 3 by 3 kernel, you get the 2D sliding DFT equation. Maybe you can follow the book, follow this source 4, which is given in the slide reference. So what is the information? What is the kernel type? This is the 4 by 4 kernel, which we got for detecting the edges. So if you want horizontal edges, convolve this kernel with the image, and similarly for you want the vertical image, convolve this kernel with the image. Okay, so you get vertical lines, vertical edges can be detected, and here horizontal edges can be detected. This is for 4 by 4. This is obtained from the sliding DFT kernel. So you may wonder that this is complex kernel. It's not a real kernel. Okay. So similarly for 3 by 3, we have obtained this kernel. So 3 by 3 horizontal and 3 by 3 vertical. This is horizontal and vertical kernels we have used it is convolving these kernels with the image gives us the certain information. So I mean the edge information, and we use that edge information. But why we prefer this STFT kernel? It performs well in case of noises, because it's a tuned filter. It can give you only that particular frequency and by rejecting all other frequencies. So the similar concept we have used for edge detection. So it's a simple edge detection methodology which is used for the road images especially. So we have also tried it for other images. It works well. In input image, take the 2D SDFT, and there is something called HDFT, hopping DFT. These are sliding DFT, modulation sliding DFT, and then hopping DFT. These are variants of the DFT. Okay, so SDFT or HDFT can be obtained. So from that, K1, K2 is fixed. For if K1 is 0 and K2 is 1, I get one edge, horizontal edge. K1 1 and K2 0, get another vertical edge. So as per the when you have the horizontal and vertical edges in the gradient methods, you have the square it and take the magnitude of it, and you get the non-directional. Here is the F, and fix the threshold, of course, and find it whether it is an edge point or not. Those processes similar, but we have the proposal is here. So this is the one which is the novelty which we bring in the edge detection process. So with this, with the proposed kernel, our kernel, the edges are this is the edge map generated. You can see the edge maps of the road images, various cases, and this is overlaying the both the detected one, and it performs quite well to detect the edges. So from this, of course, this one is you can be used for edge taking the edge information. So we have also implemented that using in a chip. I want actually my aim is to have this full ADAS as much as possible. This system should be in a chip. So this is what we are doing in the Ultra FPGA chip. So all my signal processing algorithms, whatever we develop, we implement in the FPGA field programmable gate arrays for faster processing. Mainly the parallel processing of the FPGAs can be used. So we implemented this algorithm, the convolution process, for the real-time image. So the lab environment is captured, and then the edge detection algorithm is deployed in the FPGA, and these are the edge detect, the objects of the edges are detected. This is not only for road images, it works very well. You immediately capture the image, that is real-time image, capturing and finding the image, finding the edges of the image. So this is done successfully using the camera, the monochrome camera. So the interface is monochrome, so you can see the interface of the board. And we have also used this edge detection for lane detection. So lane detection, how just I give you the steps and then the results of it. So the input frame, we made it color conversion, and the region of interest is decided, and then we use our own edge detection, the one kernels what we proposed, edge detection one. And after edge detection, we use the slow filter or the half transform to make this one. And then interframe clustering is used, and then the lane tracking is performed. These are the steps in our framework. Especially we could get the lane tracking done. So these are the steps we used in the method, the framework, complete method for the tracking. So the results I have given here. So though these images are the dataset images, you can see that this is with the shadow environment. We use with the traffic environment, okay, tracking, and C is multiple lanes. So if you have multiple lanes, it is able to track, and you have the traffic, the rules, or the writings on the road. And with no lanes, you can see there is no lane at all. It is still able to track this thing. And with the road curves, so you have this once, and then even again the multiple lanes. So these are the various scenarios. The algorithm is working fine. Also, no lane marking area with curved lane marking. You can see them as well. So curved lane markings, if there is the road curves and the shadows. So these are the areas in which we could even detect. But there is a false candidate in these cases. So where it fails, okay. So we have also detected, and this can be taken as a challenge to proceed further where it is not useful. So apart from implementing this in the FPGA of the Altera board, and we are even focused because the chip size is limited in the FPGAs. So sometimes we need the huge storage. Okay, so we have also tried these algorithms in the NA compact trio, that is National Instruments CDO compact reconfigurable input output IOs, which has an FPGA as well as which has a processor. Okay, we can either use the FPGA for implementing this algorithm, or we can even use the Intel Atom processor, which is inside. So this is about the processor. We have made use of this Intel processor of CDO. This is an experimental setup. I have given the block diagram. So the webcam unit, the environment which you use to handle this is the PC NA lab with vision development module. You need to have the vision development module and then this NA CDO. So this is a power supply, and there is a cap for capturing. You can connect the camera with that CDO, and the full processing. Your algorithm gets into the processor, Intel Atom processor, and then the image is displayed at the front panel. So the frame processing is the LabVIEW. This here the environment is LabVIEW. It's not the Verilog code, which we used in the previous cases. That is an Altera FPGAs. Here the LabVIEW, okay, you can code it in the LabVIEW, and that can be targeted for FPGA as well. But this is we are using the processor, so LabVIEW environment itself is used for this processing. So color space conversion, ROI, as I described, lane detection, and then interframe clustering, Kalman filter, and those modules are made in the LabVIEW, and the outputs are here. So you have the CDO. You can see the CDO, LabVIEW programs, and this is just for the stored image. It is shown in the here. It's not the we have done this for the captured image as well. So the detector lanes are in the front panel, shown in the front panel. So Santosh, shall I stop here or like continue?
Okay, madam, stop here.
Okay. So I have this AI backgrounds also. We have done some work on AI, so maybe sometimes later we can proceed. So
Yes, ma'am.
thank you so much here for this. I stop sharing.
Yes, ma'am.
Any questions from audience side? You can unmute yourself. You can ask your doubt. Otherwise, you can use the chat box. You can type your query. Yeah. If no more question, then sir, please.
Okay, thank you, madam. On behalf of the organizing committee and all the participants, we extend our heartful thanks for your insightful talk on the perception model for ADAS. We truly appreciate the time and effort you dedicated to preparing and delivering such a comprehensive presentation. Your contribution has been instrumental in making this workshop a resounding success. Once again, thank you, madam, for your valuable contribution, and we look forward to more opportunities to collaborate in the future. Thank you.
Yeah, sure. Yeah. Thank you so much.
Madam, can I ask you a doubt?
Ashwati,
yeah, please.
Yeah. Okay, ma'am. Ma'am, Fourier transform means we are converting the time series signal to frequency components. Fourier transform. You have used some slide DFT here. So in that DFT, you are taking the spatial information of the image as the input. Then when you are doing the DFT, you will get some signals. You will get only some series of matrix values, no? Then how you are able to convert into it a waveform, signal waveform. Then you will be able to extract that harmonics like that. My question is, from that image, how are you able to convert into that Wait.
Okay, so yeah. As I told you, again, maybe I would share. Just see, just a second. Yeah. So I just want to take space. Better. So here, so where DFT is what we get from this DFT. There is a suppose in 1D we take, we are correlating this signal information and the e power j 2 pi k by n, which is the basis vector. So when we correlate, if there is a in case of we want to extract the fundamental, so I put k as 1. Okay, so the bin index is 1. What I'm checking from this signal is if I have the fundamental, suppose of this 8 samples, this signal, my signal, and the fundamental, if I correlate these two, what is the correlation coefficient? Okay, so if it is high, that means this signal has this pattern, fundamental in that. If I say, if similarly, if I make this as second harmonic, so then I correlate k, I put k equal to 2, and I correlate these two, the signal and the what your basis vector. So when you put k equal to 2 in a DFT and check the correlation between the two, if it is high, that indicates this signal has second harmonic. Okay, so this is equally valid in images also. So images, this we are talking about in 1D, and images is having the sine and cos in both the directions. You have in the vertical as well as horizontal. That's why you have, suppose you have the stripes, the frequency variation in horizontal direction and in the vertical direction. So when we use this DFT kernels, similarly, I am focusing on maybe the edge information is k equal to 1 and 0. K1 is 1 and K2 equal to 0. So this pixels are this fxy is the image values. These are intensity values. Okay, so we have suppose 8 by 8 image in which you have 8 intensity values. This may be a 8-bit image or the 3-bit image, whatever. So depends on that you have the intensity. If it is an 8-bit image, you will have the intensity levels from 0 to 255. So these intensity levels are correlated with the kernels what we have proposed here. This is 4 by 4 kernel or 3 by 3 kernel. So when you convolve, so that means you are correlating that here. Correlation and convolution are different, whereas when you take it in the images, the correlation and the convolution, the difference is one in 1D. When we say one series, we invert it and convolve it, that is equal to the correlation. So similar in the images, we mean the same. So here is the we take the kernel and the image pixels, convolve them, so you get one value. Suppose you have taken 3 by 3 of the image. So to start with, suppose I fix it here, that means I will get one convolved value, which is this value. Okay, and then I slide this kernel again. Okay, the 3 by 3 kernel, and I convolve this 3 by 3 kernel with the image pixel, and I get the second center pixel. So similarly, the third one, you slide it over through across the image in a horizontal direction. Then next after completing the horizontal one, you get all the pixels here. And similarly, when you after completing this horizontal one, So you push the kernel to the downside so that you get the next 3 by 3 of the image. So you convolve this kernel with the image and get the first pixel and this pixel and this pixel and so on. So whereas this, because this is going to be, the kernel is complex. Okay, so it's kernel is complex. The convolved one, what you get can also be complex. Okay, so we take real and image and take the magnitude. Okay, so you get the magnitude value here. If I make k1 equal to for 3 by 3 kernel, if k1 equal to 0 and k2 equal to 1, so this the resultant ones, what we have is the pixels, the convolved pixels. Those are the values. After convolving that, we fix a threshold. So there is a threshold involved in it. So after doing this process, there is a threshold which, as usual, you do the convolution process in the with the images. Same thing. You have the matrix, every pixel value, the matrix values are taking convolved with the 3 by 3 and get one output at the end, and that one output is replaced with the center pixels of the image. That would be the output image. And those values are compared with the threshold, and then you fix whether that is edge or not. Okay. So in this, we use this is using the MATLAB code. We have coded it for the MATLAB. So this is not taking the DFT of the built-in function of the MATLAB. So we had written our own code for this, using this equation, sliding DFT equation, and we extracted. If you substitute those pixels, sliding it, and you will get the f of x k1 comma k2 pixel values in complex. This is of course a complex value. Have I answered your question?
Yes, ma'am. Thank you.
Yeah. Anything?
Thank you, madam.
Yeah, thank you. Thank you so much.
Dear participants, our session will resume after lunch, right? The session will be take up to 4 o'clock. Okay. 2 to 4 o'clock. It's completely hands-on. So we will meet in the lab session. Okay. Yeah. Thank you.
Thank you, Santosh. I'm leaving. Huh?
Yeah.
Yes.
Thank you.
Yes,
Thank you.
Thank you, madam.
You can also.
Good morning, sir. Sir, Iman, sir.
Yes. Am I audible?
Yes, sir. Yes, sir.
Please
1
tell me
minute.
the voice is clear. Okay.
Clear, sir. Clear. Sir, 1 minute, sir. Okay, sir. Good morning. Good afternoon to all. Ladies and gentlemen, it is my honor to introduce Dr. Himanshu Singh, who serves as an assistant professor in the Department of Electronics and Communication Engineering at Amruta Vidya Vishwapeetham, Coimbatore. Dr. Himanshu holds a bachelor degree in Electronics and Communication Engineering from Madhav Institute of Technology and Science, Gwalior. Master's and PhD degree in Electronics and Communication Engineering from IIIT Jabalpur. Dr. Himanshu Singh worked as a postdoctoral research associate on an ICMR-sponsored project at IIT Indore. He has served as an headache assistant professor in ECE at NIT Surathkal and NIT Tiruchirappalli. His research interests span several areas including image processing and cyber security, image processing and computer vision applications, digital signal processing, machine learning, deep learning techniques, biomedical signal processing, and evolutionary techniques. Dr. Singh is an IEEE professional member and has contributed significantly to the field with over 38 publications in international journals, book chapters, and conferences. Please join me in welcoming Dr. Himanshu Singh as he shares his expertise and insights with us today. Sir, over to Himanshu, sir. You can continue. Sir.
Okay, thank you. Thank you for the nice introduction. I am just about to start, and due to the lag in the network, I'm creating. I hope my voice is clear, and I am sharing my screen.
Yes, sir. Yes, sir. Your voice is clear, sir.
Yeah, I think it is saying stop sharing. Oh, okay, I think I can share my screen. Okay, thank you. Okay, I hope my screen is visible, and I hope my screen is visible and slides are also moving.
Yes, sir.
Okay, thank you.
Yes.
Yeah. So, so first of all, I would like to tell you that this is a kind of hands-on session. I will try to discuss the Python-based codes, means just very preliminary things related to the digital image processing. And currently, I am working in the Amrita Vishwa Vidyapeetham. This is my introduction. Already, Dr. Santosh has given very nice introduction for me. So I am just switching to the topic, and in this session, we will try to code a few basic things, and here we will use the OpenCV library that we will see. And before that, just a glimpse of image processing I would like to discuss with you. So this is a book which I have started. I have referred many times, and this is a wonderful book. You should, if you are new for the digital image processing, you should also go through this book. The best part is that if you are good in MATLAB, then its MATLAB text is also available by the same authors. So the corresponding articles which is written in this book are correspondingly implemented in the MATLAB also. This is for those who are having a good command in MATLAB, and those who are not even having the good command in MATLAB or Python, if theoretically they would like to understand, then also this is a very nice book. Already many of us are familiar with this book. So Gonzalez and Woods, and detail image processing. So I would like to start the few things about this image processing and image analysis. Mostly I have worked throughout my research in image analysis and image. So just I would like to say about a few words, like how these things are related, and there are various parts, various subdomains in the image processing, especially detail image processing. Like image acquisition, when we are acquiring the images, we are registering the images, and when we are doing the image enhancement to quality improvement of the image, and then you can also say the restoration of the image. Similarly, the image compression, image segmentation, they are also having their various applications. And compression, wherever the data, because everything is data limited, so definitely compression is having its own place. And segmentation means if you have to, instead of multiple levels, if you have to show your image in only few levels to make it understand to the computer or machine, the image segmentation is very much helpful. So broadly, we can say the image processing is consists of these five subdomains, and along with that, when we talk about the semantics and scene understanding, along with the object recognition, automatically by the computer without human interpretation, that usually most of the days, most of the people nowadays they are preferring when they are talking about the deep learning, machine learning, all those things. So in this manner, if we will see, the image processing and computer vision and pattern recognition, these all things are highly related, highly correlated. We cannot keep them apart, because to get one kind of excellence, others can be the building blocks. So it is that kind of scenario in this image processing. So that's why few basic things which are listed in this slide. Every image processing engineer or every image processing researcher should be comfortable with all of this. And this is a kind of application where object detection, just few applications I have listed in few slides, just to get a glimpse that what in which domain we can move forward to work, even for the research or the project based work, whatsoever you are doing. Object recognition and object recognition, that nowadays everybody is familiar. We are having some trained models. We can do the transfer learning also. We can create our own model also. Depending upon features also we can do, that is machine learning. And one is the content-based image retrieval, that nowadays very much familiar after the commencement of the artificial intelligence-based GPTs and all. Now Google also have created their own things, and now the content-based image retrieval is one more thing that is that people are doing these days. Along with that, biometrics and several applications in this biomedical image processing and all those things are also there. So these are the few topics over which the people are currently working, and they are continuously working from many years, and even the excellence is just coming, and now some new subdomains also opened like that. So super resolution means if you would like to improve the quality of the image and all things, means to make the normal image to the high resolution image, that is super resolution. So these kind of applications are there. There are numerous applications, and I think nowadays everybody is simultaneously using all these things. Because whatsoever is written there, this is a part of our daily life nowadays. We are scanning the QR codes. We are doing the payment. We are doing some medical diagnosis. We are using the CCTV cameras for surveillance. We are doing the autonomous driving cars. Every time we are taking the pictures in our phone, we are trying to use some filter. We are trying to get its better quality. So nowadays this digital image processing is a part. Means you can't say that this particular application is outdated or any that kind of thing. So that's why there's the importance to work here. And this is just a brief slide that there are multiple levels in the image processing where you can enter, like scene based, object based, group of features. Then if you are doing specifically feature based, means some dedicated features, if you are, so the both ways, top down and bottom up, though both approach is equally important. So this is a part of nowadays image processing. Along with that, I would like to say, whenever we talk about the image and its intensity values, we usually talk about the visual scenarios or visible light spectrum. But along with that, the hyperspectral images hyperspectral as well as multispectral images are equally important in various domains, where the intensity is in some other domain. So, and we will try to map the gamma ray or X-ray or ultraviolet images into the visual range, and then we can process it, and after that we can convert, we can derive some conclusion, derive some observation, and all those things. Nowadays people are working in hyperspectral images also, especially for the case of remote sensing and satellite imaging, etc. Even in medical imaging also, the hyperspectral images are having their own place. So these are the few things that everyone should know, that there are the multiple things to do in the research and all. And now I would like to switch to the very basic understanding before we start our coding, that what is an image in just a very simple format. We can say it is a two-dimensional view, or so two-dimensional matrix is sufficient to show a grayscale image. And similarly, when we overlap multiple two-dimensional images, multiple grayscale images, and we are correspondingly giving them in particular regions like red channel, green channel, blue channel, so we will get our RGB image or colored image. So this is the beginning of how we can map the image with a matrix, and the corresponding things we can see. Mostly if you are working on the 8-bit image, then total possible levels can be 2 raised to power 8. means starting from 0 to 255 intensity values, and that is means total 256 intensity levels are there. These intensity levels will tell us that how much the image is darker or how much the image is lighter. So these are the 256 shades of gray, which is telling us that our visualization, how the grayscale image is having the information related to the intensity as well as the edge and all everything. When most of the things when we process, we convert our colored image down to the 2D image or the grayscale image, and to observe the scenarios. That's why although directly nowadays we all are not using the grayscale image, but still the grayscale image is very much important for us, because whenever the processing, most of the contour based, texture based, intensity based, edge based, morphological processing, any kind of processing if you are doing, mostly we usually downscale our image from the 3D model to the 2D model, and then it is easy for us to understand the things and to process the things. So that we will see in our coding also. This is one last slide as a theoretical slide. After that we will just jump to the Python and OpenCV, and then we will see the codes only. So here I would like to show you that this diagram is again from the same book, Gonzalez and Woods. Most of you are familiar, already seen this. So what is the thing here? It is if you are having a 2D image, then this 2D image X and Y axis, they are showing the location of the coordinates or location or the coordinates of the intents of the pixels. Pixels are the picture elements that nowadays everybody know. Suppose we have divided your image into 100 by 100 pixels, then a kind of a square image, then they are having certain intensities. So that intensity is we are showing in the third dimension in one sense. So this is, although it is just our 2D image only, but this is to understand that what is going on. This X and Y, they are saying the location, and the intensity value is telling us the intensity level at that particular pixel element location. Okay, so that's why it is important. So till now we have discussed a lot of things here, like how the image, and we can see, and mostly the 2D image, because whenever we have to work on the color images, we come to the grayscale image to operate over it. So this is a, and in the bits format also you can calculate the size of the image, because to just show each and every pixel element, if it is a grayscale image, we are using 8 bits in one sense, just to represent each and every pixel. Okay, suppose you are saying that intensity value is 255, that means you are having the 111 up to 8 ones, that is representing that. So in this manner we can jump to our size of the images also. Number of pixels multiplied by the total number of bits used, that will be the number of bits required to store that particular image. So in this manner the size is also related with our grayscale. So actually the theory is infinite, and but I am more interested to cover it in the OpenCV model for the Python based detailed image processing. So I am just stopping myself to discuss the theory, and maybe many of you are already familiar with the theory, or even if you are not, you can go along with the code and you can understand a few things, and later also you can go through some book to understand a few more things. So just I am jumping to my environment, like I personally I am using the Spider. Nowadays Jupyter also people are using, and also lot of n number of IDEs platforms are there where the Python based programming people are doing. But just to see the few things, I myself have used the Spider, so I am trying to take you to that particular environment. So this is the Spider environment. If you would like to see when we open the Spider blank, so it usually looks like this. Already maybe many of you have done this thing. So just I would like to share a few things before we will starting, because maybe you people are having some other IDE, but for the now, if we will go to the installation of some other IDE from the scratch, it can take time. So my idea is that I will try to show you code by line code in this IDE. try to bear with me, and at the last I will share the complete Python file with you also. So so after this session, you can also run it by yourself. And better both things are possible. If you are having the Python already installed, you can type along with me also. And if you are not having, then you can use the Google Colab or some other online Python platform. That is also possible. And if the both of the things are not possible for you, so the thing is that line by line you can focus, and later after this session you can go and install and run the Python over your system. So anything is okay. The main purpose is that you should know that how the things are so easy, because whenever we jump to any new coding or thing, we should know that how the things are related, what we already know, and how the people are doing the same thing in this particular language. That is basically the idea of any code dependent or language dependent or programming dependent session. So that I think that is my thought. And so I am just actually I have created one script, although these things are very this script I have created, and I would like to discuss with you just line by line. So what I will do, whatsoever thing I have to discuss, I will share this script with you people also. Whatsoever things I have to discuss, I will just uncomment it. Here in Python, we usually use the hash to comment the things, and I will uncomment it, and then I will try to run this, and I will show you the corresponding outputs. Before that, as we are working in this image, as we are working in this, we are working for the image. So I have taken few images. Just I would like to show you in that thing. So before anything, I would like to just show that. Oh, along with this code, you have to keep some images also, because then only we can read and write the over images. So like in this manner, I have taken 2-3 images just for sample. Like this is the one a cat image where multiple cats are there, and then I have taken a chess image, then one more chess image. Okay, so mostly I entire my script I will use over these images also. Along with that, one more video I have taken. So this video, although you can use your webcam also to take the video, but here I have taken a pre-recorded video in the MP4 format, .mp4 format. So that we will use for our coding. So along with that, one Python file is there that I will share with you. So these images, videos, and Python file, everything I will share with you. So what will happen? Just line by line, I am trying to run this code, and I am trying to discuss few things. If you are already known the Python and OpenCV and all, just try to be with me. Maybe many of you are new to this. So by the end of this session, we all will be on the same page at least. So that is my idea. If you are having Python, you yourself can start the code, and you can write the codes, and you can get the outputs in the real time. Otherwise, later also you can do the same thing. That is not the problem. And also, this is very I have listed very basic code lines and very basic programs, and that will be useful for the other sessions also. Means throughout this FDP, maybe other people can also tell about their presentations and their expert talks. So the same, this is very basic and preliminary. So I am not going to the very high level. So just I am thinking that my listener is very new to the Python as well as the OpenCV. So in that with that motive, I would like to start my things. So first of all, the first task is just to read how we can read the image in OpenCV. Oh, okay. Before that, before anything else, I think I should show you one website, that is the OpenCV library. OpenCV library also already it is a cross domain or cross language library already created, and here we are using its Python equivalent only. So that is the thing. And here we are using this OpenCV model. And here, if you would like to go there, then it is actually everything, the Python and related things are open source. So there is no need to be any license and all. So just go to this OpenCV website, Then you can go OpenCV tutorials. This is cross domain. And then specifically for the Python, if you have to see, you can just click on the OpenCV Python tutorials. Then lot of things you yourself will get. And here everything is given better than me also, means whatsoever I will explain you maybe better than that also. Here already it is existing. So that also you can explore after this session. So this will be very much helpful because code wise everything is written there. So then if you will just suppose open it like how to install and all, starting from that, just you can jump to the image processing and then multiple types of the coding, the related theory, everything is given here. So this is a very good thing that if you will start copying line by line or typing in your IDE, and you will get your thing to learn. But okay, here if you will follow, you will find complete in a complete manner the complete image processing and related things in an organized manner. But my point is that just in 1 hour, if we will try to cover, then I have taken few snaps or few codes out of it, and then I would like try to discuss all those things. So this is your report. This is your kind of dictionary where you can go anytime, and you can in the free time you can go and just learn the things. This site is very well helpful. Along with that, other tutorials are also available, but this is kind of the original documentation by the OpenCV people, so that will be better for you. So now I am again coming to my this spider window. So here in this spider, we are having this kind of environment. For those who are new to the spider, they should know that there is one console window. This is more like our command window in the MATLAB. And here we are having the variable explorer, plots, files. These all things, files means which folder you have opened. Here you can go. And similarly, the main thing is that if you are running a file and corresponding requirements, means like the image is required and all, they should be in this particular folder. Otherwise, we have to give their path also while reading them. So that while suppose, because here actually if you will if you will see the first line, okay, I will start with the first line. It is the CV2 library. Just you can import it as a CV also. It is your opinion. It is your choice. You can give it any short name also, because every time you have to use it. So I have taken CV. You can take directly CV2 also. If you will remove this import CV2 as CV, the only CV2 if you will keep, then everywhere in the commands you have to use the CV2. That only you have to take care. So similarly, the things will be like this. And but I have written in this manner, like I have imported everywhere CV2 as a CV, and then I have run these commands. So this is the first thing, first line we have discussed. And second line, if you will see, we are reading an image, and that image should be in our current directory, first of all. So that you can check just by clicking on these files whether this image is not there, this image is there or not. So if you will see, this image is already there, the real_chessboard.jpg. So because it is already available in my current directory, I don't have to give the path. Otherwise, what we can do, we can just copy this path, or if some other library, if some other place in your machine, if you are having that particular image which you would like to read, then this complete thing you can copy and you can keep it in front of it, so that the complete path of the image you can give to this command. This is how you can read any image. So I am just coming to my variable explorer. Once I will run only first 2 lines, suppose I have commented all other script. So whenever I put this run button, then only the first 2 lines will get executed. And once they will get executed, then you can see here, we can see the variables. So this variable img is a dummy, img is a local variable that we have created. This variable is an array of uint8, because I already told you, if you are using the 8-bit image, means your intensity levels are ranging from 0 to 255. That is your uint8 notation. And what is the size of this image? Because this is the color image. I have already shown you that chess image, that was the color image. Because the color image, so RGB 3 channels are there, or BGR, any one sequence you can tell. So it is the size 390 rows, 600 columns, like that. And the third dimension is 3, means 3 channels. So it is the thing. And if you would like to open, and if you would like to see, then up to some levels, you can, up to something, you can observe that what is going on for means index by index and all other things, you can see that it is a complete matrix of means it is a matrix. It is actually a 3-dimensional matrix having 390 rows, 600 columns, and 3 width, you can say, or depth, you can say, and any one word you can use. Like you can say height, width, and depth. In that manner, you can people usually use. So in this manner, you are taking a colored image and you are storing it in the img variable. Now, in this manner, you have taken this image and brought in this environment. Now you have to show it. Suppose then you can take this third command. You have to show. So cv.imshow you can do. Then this is the name which you are writing is just a tag name. This will come over the image, and whatsoever image you have to put, this will come as a header of that particular inset or that particular window which is representing your image. And this img is actually of our prime importance because this is storing our image. Okay, and one more, and nowadays in advanced IDEs, this is not required that to show that you have to use this CV wait key. Otherwise, in conventional CV open CV library, it is a wait key which is telling that if you are putting it for some milliseconds, then if you would like to keep it open for few milliseconds, after that it can automatically become off. All those things you can do, but just for safe side, my habit is that I always just after IM show, I usually keep this command. So the 0 means it will remain open till you will not close it, like that. So this just one image we have first read, and then we have tried to show it. And along with that, IM show is means just now I told you this is just your header name, and it is just a kind of tag, and it will not affect your other things. So originally the name of your image is img, but it is here the header, anything we can change. So this is just to show as which header your image is going to show, or image is going to be displayed, like that. So this is the first part. Here we have read, and here we have read, and then we have tried to show this particular image. This is the first 4 lines was for that purpose. So just I am trying to comment it again because we are trying to go for the next part of the code. So in the next part, what we are what we have done here, our objective was we have read an image. Then after reading the image, we have shown it in its original form. Okay, so if it is a colored image, then the color image will be shown. If it is a black and white image or grayscale image, it will come in that manner. Now we are trying to read an image, and then we are trying to show it in the grayscale form. So for that, again, we have to follow the same kind of scenario. We are importing our CV2 and we are renaming it as a CV. Then IM read we are using. Along with IM read, there are multiple associated parameter or values which you can use. That here in OpenCV directly this CV underscore IMRE read underscore grayscale command is there. So by this, if you once you run this command, that automatically your IMG value will be the. Now suppose if I will run it again, it will automatically become okay. I am running only for first 2 lines, suppose without showing it. Then if you see, then here previously it was a 3 array. It was a 3-dimensional array, or you can say the 3-dimensional matrix. But now it is just a 2-dimensional matrix. So here, just by this command, your colored image is now converted into the form of the grayscale image. And then this grayscale image, if you would like to see it, you can just uncomment it and you can run the code again, and you can get that the corresponding grayscale image of that colored chess image is visible to you. Okay, this is the second. This is the first part, and the first part we have means we are trying to show our image. Along with that, if you would like to know that what else we can do and how this function can be used, then for any function you can type the help here, or many other options, many other pop-ups, many other drag and drop options are also there. But this also you can use. Just if you will see, put any function which we are using in the OpenCV, or means cv.imread, and put it in the brackets and keep the help before it. And once you run this, then you will get the complete information about this function, that how we can use, what are the possible values, and what are the things we can use. Okay, if you would like to undock it, you can undock it also, and you can see the complete things in detail, that everything is written, that what kind of name value pair you can use here, then what kind of images you can show it, like the JPG format, PNG format, whatsoever things are there. And some instructions are also given for. So it is, whenever this library has been created, this complete information whatsoever the design, the those who have created these functions, whatsoever instructions they would like to convey, they have already given this. So that's why anytime if you are getting confused, or if you would like to know more about that particular function or keyword, you can say, that it is a very good habit if you can go to its help, and you can see that what can be done, how it can be used. Like if you see here, for the grayscale also the things are written, that when using the IM read under grayscale, it will convert to the grayscale conversion, and grayscale conversion will be there directly without. So why it is important? That means if you would like to think in a broad manner, then one more thing I would like to say here. In the previous case, suppose if we have to use our image in grayscale only, and then we have read that image, take that image in the 3D, and then we have converted it into the 2D, suppose, then it will be a long process, and unnecessarily we are taking a lot of space. So better than if we can directly use this command, then what will happen, although your image is 3-dimensional, but when it comes to the picture, when it comes to the storage, only directly this command is converting it into a gray. So now, although this is very small thing and very less memory it is taking, but the same code, same Python code, if you will run on some resource constrained device, like suppose on Raspberry Pi or some other mini computer, or some nowadays lot of mini computers and all those things, wearable devices people are using. So that at that place, the power and size and area, everything matters. So that's why such kind of command, such kind of script writing is very much useful, so that in very less lines, very less conversions, very less data usage, you can just serve your purpose. So that's why it is important to know more about the keywords, because everybody knows that you can read it in the color image also, then you can convert it into the grayscale image also, just one more line you have to write. So every time we have to think in that manner only, that manner also, that how our programming can be more efficient and more resource constraint devices, which means it can run better on the resource constraint devices. Okay, so that is one more thing. So again, I am commenting this second part also, and we are just jumping to the third part. In third part, we are trying to read in third section, we are trying to read and video. How any video can be seen, and what is the things. Actually, whenever we see any video, the frame by frame, we have to capture it, and frame by frame, we have to show it. And just one frame after another frame, it will go, and that will look us as a video. So what will happen, already one video is created, that hand move. So first it is reading, first it is capturing that video. So what will happen, what is going to happen here, first it will read the video, it will capture frame by frame, then that frame by frame it will show to us. So although it will be like one frame after another, it will be playing, but to us it will look like that a video is getting played like that. So for capturing this CV_video capture, you can use, or if you are not using this CV, then directly import CV2 command you are using, then it will become the CV2 dot, because it is the function of this CV2 library. So CV.video capture, this command you can use. Inside it, you can write your video's name. Like if you see it here again, like we are having one video here with this name, and hand_move, then .mp4. So the complete file name with extension, you have to write it. Then what will happen, we have to create a while loop to show it. Why? Because we are using the IMShow command to show it. But IMShow command we usually use to show the image only, just one frame. But we are using this in a while loop format. So if we are using it in the while loop format, and we will put some wait amount here, and it is just for conventional things. But nowadays IDEs are so much developed with that that yourself it itself will stop your video once the frames will be over. So, but still we should know that that why these things are required, and along with that, one by one, because because multiple frames by frames, it will show that previous frame should be closed also, and no other cache memory should be created, and all those things we have to take care. So the destroy all function is also there. Although nowadays, if in advanced IDEs, without using this also, we can get our purpose served. But the main thing is that how we can capture the video. Then once we have captured this video, then frame by frame, we can process it as an image. So that is the most important thing to understand here. Like instead of this cv.imshow, you can also do some other kind of image processing operation in place of this particular line. And suppose you are denoising the complete video, you are enhancing the complete video. So frame by frame, you can do this thing, and this complete thing will go in a form of the loop, like a while loop here. And so what will happen, if means whatsoever image processing you can do it over the video process as a video processing also. That's why this syntax is important. So I will try to run this code, and once I will run, you will find that frame by frame it is looking, and your frame by frame it is showing, and it is looking like a video is playing. So this is the thing. Okay, so this is the one way how we can read and how we can show our videos. Now we will jump to the next section. Here we are trying to resize and rescale the images. So okay, first I will uncomment it, then line by line we will discuss about this code. First of all, we are importing the library. Then I am clearing this variable also, just to show you that what else will be there. So now we have cleared. You can clear your console also, just to avoid the previous things if you don't want to see those. Here, first of all, we are reading an image, and this CV I am read unchanged. It is one more name value pair that it is one more syntax that it will remain as such, means it will not be resized. So we want to see it in its proper original form, which is available. Then after that, we will try to show it. So this is the one part. We are reading an image, we are showing an image. Then we are also printing its original dimensions. So this original dimension, which is written in the green, it is just a tag. And so when we print this string will get print. String whatsoever is written in green here, it is an string, and that string we are giving in the quotes, in single quotes. Then after that, we are putting the comma, and then we are putting the image.shape. Shape is a property of the image. So image is our variable. It is a matrix actually. And what is its size? What is its shape? It will come as a variable image.shape. So suppose if we will print this, then what will happen? This IMShow will show your image in the visual form. This print will come to the console, and here your things will get printed. Like what is the shape of the image that will get printed. So I think before anything, we should run this part of the code. So I am running only this part of the code. Just so if you will see that this image has been popped up, and after that, if you will see the string which we have written here, the original underscore image. After that, original underscore dimensions colon. This is a part of the string. After that, this variable which the variable is given is image.shape. So what is the shape of this image? You can go here. You can go to the variable explorer. Just a minute. Okay, it got cleared. So okay, so once if we will run this, just a minute. I'm running it again. Yes. So what will happen? if you the original dimension, if you will see, the original dimension is 390, 600, 3, means it is a color image, so its dimensions are looking like this. This is the one part. Now after this, we are just uncommenting the second line. It is like how much we would like to scale in the percentage form. So for that, we have taken one scale percent. Like usually we resize our images like 60%, 70%, 50%. So means we are reducing the image. If we are trying to make it bigger, then we can take it to 160%, 600%, anything is possible. So just to this code has been written in a generalized manner, both for rescaling, means to the bigger dimension, to the lower dimension, both things are possible by using this particular code. So after that, we are trying to write a width and height variable. In this width and height, what we are doing, this image shape, if you will see, it is a vector which is having 3 values. So its first value is the height, second value is the width, any one thing you can say. So this width and height, we are just putting it the percentage, we are multiplying it and dividing by the 100. So what will happen, this 390 will get multiplied by the 60 and divide by 100. So what will happen, total first previously 390 rows were there. Now instead of 390 rows, now it will be 390 multiplied by 60 divided by 100 rows. So it means the 60% of it. Similarly for the height also. Now the new dimension will be width, height. Just now we have created them. Then we will use our cv.resize. This is the command which is doing the magic. So this is the most important. This is the only command which is working here. Like other things are just to keep your inputs and outputs ready. So this image, then dimension. This is one more way to write the code. Like you have given all the parameters previously, and like dimension already you have shown here. Otherwise, directly this width, height also you can write here in the brackets. That will also work. Then interpolation, because when you use when you will increase the size or decrease the size, sometimes definitely you have to use the interpolation also, and that interpolation are of multiple types. So I am not going inside this complete interpolation and everything, but if you would like to see, again you can follow the same way. Like you can, okay, once I will close it, then that part of the code will get closed, and here you can see now the variables are also visible here. Okay, so here the same variables are written here also. That is one more thing too. And whenever you have to see the more things about any function or keyword, it is a good habit if you will use this help. And again, you can undock it in the big banner, and you can read that what is going on, what kind of interpolation, various kinds of interpolation are there. Then that you can use, you can study in, you can read about their mathematics and all also. So that we are not focused for that particular thing. But suppose you are using one particular kind of interpolation, then after that you are just printing the resized dimension. Resized dimension means because you have changed the dimensions, then your dimensions, the new shape will come, resized dot shape. That resized it is your new image. Then we will try to show your resized image also. So what is going on here, if we will see in this complete program, 2 visual outputs and two numeric outputs are there. Okay, print command is for numeric outputs. Those numeric outputs will be visible in this console window, and when you will use this cv.im show, that will pop up as the image. So that we will see how it will work when we will run this code. So if you will see these original dimension as well as resized dimension, it is written here. So as we have given 60%, so this was the original image. It is written here also. That's why the tags are important. Like here we have written in as a form of the tag that what is the name of the image. The name of the image means tag of the image. That will be the header in the Windows usually. So what will happen? The resized image is written here. So this is the resized image of this original image, and the 60% view is visible to you. So we can also do and also along with that, the original dimension as well as the resized dimension also get printed here because of these two print commands. Okay. After that, suppose I would like to increase the size of the image. Instead of 60%, I am taking it 160%. So if I will take it 160%, if I will run this command again, then what will happen? This is your original image, and this is your 160% of that image. Okay, and here means the size of the image got increased. So, and I think you are able to see without any pixel, without any like pixel stretching, here properly we are getting to obtain this image, because obviously when you are stretching an image, your original image was in the size of this 390 cross 600, but because of interpolation, because you have stretched it to the 624 to 960, so definitely in between pixels you have filled by some equation, by some rule. So that rule is useful. That's why that rule is dictated by this command, this interpolation command. That's why this is important, that which kind of interpolation you are using, like polynomial, like cubic interpolation, spline interpolation, lot of other definitely averaging interpolation is the first one which we usually read in our school level mathematics and all. So a lot of other interpolation things are there. We are not going in detail. That is another field that which interpolation is better for which kind of environment and all. So that is one more thing. We are not going inside it. This section was dedicated only to understand how we can resize and rescale our frames. So that is the one thing. So now I am again commenting it. You can also, once I will share this code with you, and then you can also run in the section wise mode. Also, you can put this section wise in the Jupyter window also. That will be very easy to understand. That also you can do. And here now we will come this for the same thing, but we have done for the image, we can do it for the video also. So if you see this command, if you one more thing is new to you, if you are new to Python, here we have used some defined functions. So here some local functions we have created, and then these local functions we have used, we have called these functions, and on calling these functions we have used it, and we have used it, and we have rescale our video or resized our frames. So here what to understand is that if you have to rescale any frame, then first of all, the width and size, width and height, as the previous case, dimensions also written. Then this cv.resize, this is the core function which is already available in this cv2 library that we have used, and we have redefined our own function with this 0.75 of scaling. Okay, so what will happen whenever we call our this function rescale frame function, this function automatically knows that you would like to rescale only up to the 75% of the image. So without, that is the part that is the thing, that how we can create our own functions and using the previously defined functions. So here all this width and height and dimensions are given, and interpolation method also given. But now if you have to call this function multiple times or very frequently, you can just give your frame, you can just pass your frame in this, then it automatically knows frame by frame, for each and every frame you have to rescale it to the 75%. Okay, just 75% we have taken. You can change it for your according to your opinion also, no issue. Then what will happen, while this while loop as we have already seen, just to show the videos, that how the video frames will go one after the another, how the video will get streamed. So that is the purpose. So now I am trying to run this code, then you can see that what is going on. Just a minute, maybe some, okay, we have changed. Okay. Some error is there. Okay, we can just cross check it. Yes. So actually that is not required in the new versions of the IDE. So because these are already taking care of this. So this is how the videos are looking, and the video has been already also resized. And if you will see, if you would like to see, then we can put it in this format also. So in this manner, we can resize their videos, and we can store these videos also, and then we can play it from their position. When whenever we are using this im read, the corresponding im write command is also there, imwrite. So that command also you can see, and you can put it help here, like cv underscore cv dot imwrite. Here you can see. So and then you can see this the complete thing is written, that how we can use this command. So this command is useful if you would like to save your processed image. So means here we are not having means after processing, if you would like to store your image in that particular library, in that particular location, suppose this is your location, this is your you can say the directory. Here you would like to store some image, you can give the new name, and you can restore it. If you will not give the new name, it will replace it. So just take care of that. Okay, so this is one more thing, that how we can resize the videos and all. So that is the one thing. And now we are just jumping to the next section, and here we are drawing some shapes on the images, because that is important when we do some good processing things called quality comparison. Then this thing is very much important. If you want to annote, if you want to put some symbol or some line or some shape on the original image, so that we will see that how we can do. For that, one specific command is there, cv underscore line. If you have to just draw a line in any orientation on the existing image, then this line, this cv dot line command you can use. So that we will see here. Here, just if you will run this code, we have used one more library. Just I would like to show 2-3 things in this code. That's why I have run it before, make you understand. What is this? First of all, we have imported the cv2 library. Then we have used the numpy library also. Numpy library, very famous library. Most of the people are knowing that it is for just taking the arrays, and because our how to deal with the arrays as a whole. So in as we see that our matrix, our image is a matrix, and sometimes it is a 3-dimensional matrix, multi-dimensional matrix, or at least a 2-dimensional matrix. So that's why the how to deal with the arrays are equally important, and we can use this numpy library also sometimes for according to our purpose. So here this numpy library just we have used to create a array of zeros of this size 512 and 512. What is the thing here to notice is that along with the line drawing, I have just appended 2 more lines here. We are creating a complete matrix. We are just trying to show a complete matrix, which is an all zero matrix. All zero matrix means it is having all intensity values 0. That means it is a black in color, and that we are trying to show. So these second last and third last line was dedicated only for this particular blank. And then if we will forget about it, then what was the purpose of this section? This just to understand how the cv line dot line works. So it is actually whatsoever line you have to draw over the over any image, that first of all you have to give its color. If you have to give its color, means it is in that format, BGR format, blue, green, and red. So this is the pattern which is getting followed in this OpenCV. Unlike the MATLAB, in MATLAB usually we see the RGB sequence, but in this CV2 we have to follow the BGR sequence. So that is a little different thing. Along with that, as we know that that some specific command is for red and the blue and green. Like if suppose if I will uncomment it, then you will find, if I will run this code again, just let me close it and then I will run it again. So then you will find this, the line which was blue earlier, now it is a red line. So how we have done this? Because this different color code we have given here. So this standard color codes you can find on the internet also, specifically dedicatedly for all the possible colors. So but just for red, green and blue I have listed. I have made the other two commented just to show one by one. And along with that, we are giving some dimension, some locations. If you would like to see its help, that also you can do that. How this is working? Like here you can type the help, and you can just go to this particular yeah, and E. and then we can put it enter. So if you will see that it will tell us that from where to where it is, the means like PT1 and PT2, because just to draw a line we need only 2 points. So the location of the points can be shown in the form of the coordinates, because we are working in the 2D space. So these are the coordinates 100, 100 and the 300, 300. The same thing I have shown you in the slide also. If you remember, I have shown you this slide. In this slide, it is visible that we usually start our coordinates from this top left corner. That is important, because how many pixels you have to count, that is okay, but from where to count, that is required. So this is the origin in our detail images. Usually we take in that manner in Python also. So like OpenCV also work in the same way. Here the top left corner we consider as a 0, and we start from here. So if this is the origin, then our point 300, 100, 100 will be somewhere here. 300 means somewhere which is equidistant from both the axes at the distance of 100 pixel. So in this manner we can see, and similarly we can get our 300, 300 point also. And at the last we can say we are just drawing a line starting from 100, 100 and landing up to 300, 300. Okay, and so obviously if you will see, this will come as a just 45 degree line. So that's why this line is in this angle. Means like if you can see here that if you can see here this starting from this location to this particular location, this is your 100, 100 point. This is your 300, 300 point. Suppose if we will change it, you will land to the some other location. Like suppose if I will keep it 200, it will end somewhere on the top somewhere top place, like not it will means it started from the same location 100, 100, but it ended up at the 200, 300, not 300, 300. Sorry, 300, 200 means 300 is the distance from this axis, and 200 is the distance from that axis. That is the thing that we can see. And this distance is completely in the form of the pixels. How many pixels it have to pass, and so on. So in this manner, like we have seen only line shape. Similarly, the rectangular shape, circular shape, ellipse, or any polygonal shape, everything is possible. Just for that particular command, we should know that which parameters we have to pass. So, okay, so I am commenting it again, and we are just jumping to the next part. Now we are trying to create the rectangle over the image. So that just in place of the CV dot line, you can use this, and you can make it to the CV dot rectangle. And here obviously the parameters will become different. Like unlike the case of the line, here you have to give the 2 points. Those 2 points are the diagonally opposite points of the rectangle. Means so just we will try to run, and along with it some more parameters also you can give. Same parameters you can give to the give to this line command also. Like various kind of thicknesses are there, line types are also there. You can get a complete list in that CV2 repository. If you will find here, everything you will find in this OpenCV library, that what kind of possible line types are available. So I have just taken a particular specific value, and if we will run this code, this warning is coming because we have not used this NumPy library, so we can delete it also. That is a good thing in these IDEs. They themselves suggest that what is not required. So here, if you will see, we have created a circle which is red in color. Why it is red in color? Because we have used this 0, 0, 255. So as I just now told, in OpenCV we will follow this BGR format. BGR. So BGR means blue is 0, G is 0, and red is 255. So if red is having the complete full intensity value, then the pixel will look like red only. So this look in this manner we can create our circle, create our rectangle, and this is the first point. This is the last point. The PT1. This is PT1. This is PT2. If you will give these 2 points, then you can give the details about the dimensions of the rectangle, and then happily you can draw it. As we can see that the distance from this actually this is more as a square, and you can create a rectangle also if you will change it to some other you can take it 200, then its view will become different and it will become the rectangle. So in this manner, you can go up to according to your demand. And why it's required whenever we are doing some kind of research or some suppose image restoration, image dehaging, object detection, face detection, all those things when we do, we will try to keep our this kind of bounding box over the detected object or over the thing which we would like to highlight to the viewer. That is one more thing, that if you are interested to highlight your change, your better, your excellence of restoration to the reader, that you can do that. Along with that, in case of the object detection, whenever we want to train your models that the particular thing which is inside this binding box is a human, is a tree, is a vehicle, that you can train according to the bounding box locations and the corresponding labels. So that is the thing. Okay, that's why these basic things are required. So that's why I have included it. And similarly, we can go for the circle also. We can go for the ellipse also. We can go for the polygon also. Polygon, if we will take, means we can come up to the any shape. That's why it is important. So for all those things like cv.circle, cv.rectangle, cv.ellipse, you can see their helps here also, and you can go to their documentation on this particular website also, and that you can use happily. According to everything is having their own specifications. Like circle, to draw a circle, only the center and radius are sufficient. To draw this ellipse, along with the center, the angle is required. The angle from the minor axis or the major axis, that is important. So that at least one axis, like maybe semi minor axis or the semi major axis. Along with that, the angle of the orientation of that particular ellipse, that is required. Similarly, every shape is having their own thing. So that help that we can get from the help, and we can use according to our demand. So now I will jump to the another part. Like here our objective is just how we can create some colorful patches and how we can create it on the images, how we can overlap. That we will try to see. So just a very basic code. Just we can skip it also, no issue. But okay, just means what we are doing, we are trying to just show two patches. One is green in color, one is completely black. So if you see the blank, the blank, or you can say the black, anything is okay, because there is no intensity. So we have created a zeros, and that zeros we have shown. So that is looking like a black image. And then along with that, if we will create this, like we have taken the same matrix, same three-dimensional matrix, and we have assigned these values. If we have assigned these values to this matrix get replaced, the variable get replaced, and now the 0, 255, 0 is assigned to each and every pixel. To how it is going for to each and every pixel, just by giving these dots in the square brackets, means this these inputs getting mapped to all elements. This is very nice way to write the code, that if all the channel values are same, you can give your things in this manner also. And just now I told you the sequence will be in the format of BGR, B, G, R. That means you are giving the green value, full value. 255 is the maximum possible 8-bit value. So definitely it will look like a green. So in this manner we can show it, and this green is just the level, so that you can see that over the green window the GREEN should get typed in this manner. So this is the one more thing, and then we can create the line also, and that we will see that that is okay. And here actually if this we have renamed it, we can rename it here also. We can give this as the same name here. Then we will see, if you will run this code again, then just a minute, it's done. Okay, we have to show it also. So we are just showing it. We are actually just creating this this img. I am not changing its name. Let it be. So what will happen if you will run this code? Just close it. We will run. Let's just start. Yes. So here okay, the line is in the red color, but it is not visible. Okay, we will see it in the yes, now it is visible. Actually, we should keep this CV at this last stage wait key. So then you can see here the over this green patch we can create the line also. So this is just we have used the CV dot line. This is that much basic. So now I would like to move forward because these are very basic things. I think most of you are familiar or even not familiar. Just by a single command you can get all these things. So now we will just we will try to augment the colored patch. How we can do that we will see. Just we are putting the patch over means in one form we can say we are putting one image over another image, like as we are doing this thing for the patch, that we can do for with some other images also. And like usually we make the collage of images, that collage of images we can make in this format. Like this was our original image, and over this image we have put the three different images. One image is just the line, we have then two more sub images we have kept at the particular location. So how this is possible, that we will see. Actually what we are doing, first of all we are creating a blank matrix that is having all zeros, means it is completely black. That is done over this line number 140. After this, what we are doing, we are taking some particular selected pixel and to that we are assigning this BGR. BGR means red value. BGR. We are assigning this red value. After this, we are this is one way. This is one way how we are giving our red patch here. This red patch is because of this command. And then after this, we are creating a line. So this is in line number 117. We are creating a line which is of red color. Again, this BGR, R is 255 and other two are 0. So it will come as a red line. Along with that, we can use our rectangle, and along with this rectangle command, we can give the thickness is equals to CV dot filled. So just see, this particular parameter is making your rectangle which is filled with the color. So the same thing which you were doing here with the red color, the same thing you are doing here with the green color. Okay, so these are the two ways how we can do the same kind of thing. And here we have taken simply patches. Again, I am repeating, instead of the patches we can take some other images also. So we can make a collage of images or some other kind of thing as per the demand that we will see. Okay, so this is the one more thing that we should know. Means actually slowly when we will go through all these basic things to do, our confidence over these coding and commands will get increased. So that's why these basic codes are also necessary before going something very specific in the research. So that's why it is a good habit, I think. So now we have to put some label, because that labeling and text, put the text on the image is equally important. So for that, this particular command which we can use, cv.putText. Again, the complete help, if you have to see how the fonts are decided, there are some n number of fonts possible in this cv2. That also we can see what is the font size. That is one more thing. All other things are there. So that we can see, and we can put this cv.putText, and that we can edit like and what I am doing here, I am just creating a blank image. Blank image means complete black image, over which I am putting my label. Then another image which is our chess image. Then I am putting my one more label, that is my chess, and I am changing its color. Like previously I am taking it in the green color, and now in the chess image I am creating it in the red color. Okay, so that let's see what will happen. Okay, this previous windows I am making it off, and then we will run this. So if you can see, okay, this is the these two images we got. Yes. So this is the first image, and actually I have intentionally changed, not changed the name. So the name which is coming is as a text here, and the chess means you can put any name. That is just the name of the window in one sense, in nothing else. It is just a tag so that you can differentiate between the two different images. And here my level, this text you have printed, and the location of this particular text it is given 200, 200. Means from this 200, 200 it started its first letter like that In that manner, we can give its location, and then the font and font size we can give it here, and then we can understand. Same thing we can do on our chess image also. Means just my chess I have just typed here. We have given the location 200, 30, means 200 from this side and 30 from the top. Okay, so very less orientation in the vertical axis, so that's why it got placed over the top of the image like that. Okay, this is one more thing. So in this manner, we can type some text or some other thing. So this is also required sometimes when we would try to highlight some particular part of the image, that only then it is necessary. Now, just grayscale command, although already we have used this in some other manner, but if you have to just create your image to the some other color space, that is also it can also be done. Like here we are reading an image, we are trying to show that image, then this CVT color command we are using. This CVT color command is just to convert from one domain, one color domain to another color domain. Those who are doing little bit image processing, they should know that images we usually understand in some RGB domain, BGR domain, gray domain, HSV domain, color lab domain. So various domains of images, depending upon how the humans are understanding, various color models are there, how humans are understanding the images, how machines are understanding the images, and depending upon the advancement of this computer vision applications, people have created some different domains. So we should know that how this conversion of the domains are possible. Those all things we can cover under this particular keyword, this cv.cvt color, so that we can see. Okay, so what is going on here? First, we will import this library, then we will read our image, then we are creating its gray equivalent. Then we are along with that, I have also included one more line just to take its edges. So the canny edge, already we are knowing that canny edge extraction is one particular method. So we are taking the canny edge, we are using the canny edge, and then we are trying to show it also. So correspondingly, three different windows will pop up after this code. One is the original image, second is its grayscale image, third is your canny image. So that we can see that how it is working. So if you can see, this is your original chessboard image. Then after this grayscale corresponding image is there. Then this is the canny edge detection which we have done. So if you can see this command, it means similar to the canny, other functions are also available, other edge detectors are also there. You can explore them, and here also you can decide their values, like which these are the minimum and maximum values that usually we take as a threshold when we use any edge detector. Here in this particular case, the pixels intensities, those who are less than 125 or more than, because usually it is the convention, usually it is the understanding in a general imaging techniques that very high and very low intensity values usually don't cooperate, don't required for the edge detection, because edge detection somewhere there the change is there and all. So mid intensity values are more required to understand the edge detection. So that's why people usually discard some intensity values, as we have discarded here. The intensity is less than 125 and intensity is more than 175. So this is the way how the canny edge detector and all they works. Now we will jump to the next part of the code, that we are going to blur an image. Okay, sometimes it is required and sometimes it is also required to show your excellence of the restoration method. So that we will see. Already this thing is written, so I am deleting it. Okay, so now what we are doing, we are just deciding a kernel size. Kernel size, whenever we have to do any processing over the image, we usually choose a window, and that window we usually move over the entire image, start in both dimensions. So that is the usual way whenever you do any kind of filtering or any other thing. Gaussian blur means, here Gaussian blur we are using. We, in one sense, you can say we are also doing some kind of smoothing. And when you do the smoothing, or those who are good in filters, then we can say the low pass filtering we are doing. So when we do the low pass filtering, our features will become blur, like because low frequency components will become dominant. and similarly and vice versa case in the high pass also. So here when we are doing the Gaussian blur, in one way we are doing the smoothing. So the Gaussian blur, just this CV dot Gaussian blur you can use, and the kernel size and this sigma x value, and you can give it somehow less and somehow more also. It is just how much variance of this particular window you have to maintain. Okay, so if just we will try to run this code if it is okay. Okay, we have not okay, so better if we will use this command also, because we have not imported the library, and just over this command means after this command these commands will get appended, so the complete purpose will get solved. So let's see what will happen. This is the dashboard, this is its scanning, and this is its blurred image. So the somehow blur is there if not visible properly. This is very much high definition image it is looking, and some kind of blur is there in this particular thing. We can increase or decrease this blur also. You can change the size also. You can change this size to make of 15 by 15 also. Then also the effects will be visible. Just let me close all of them. Yeah, just here one more is there. Yes. After this, if we will run this, you can see the blurring is to the next level. Means like in the as the previous case, if we will use the more size or the variance, we can change the blurring will be different. So this is one more part which we have seen. Again, I am commenting these things, and we are going to the next part. Then here we will discuss the transformations. So some translation, rotation, flipping, all those things we can see. So here, first of all, we are trying to show this translation. Translation means you are trying to move the image in some particular direction. So here, if I will uncomment it, and if I will just, we are importing the library, you are importing the NumPy library also, and then we are trying to show this image. After that, we have created our own function. And what is the purpose of this creating own function? Then nothing, but just what kind of translation and in what dimensions you have to follow, that you are giving already. And then if you are giving it here, then CV underscore ref affine. This is the particular command which is doing this. So in this directly this command also you can use, and you can give your input as a parameters to this particular function. Anything is fine. So now after this translation, you can use this, and that translated image, because this translate function you yourself have created. So here the input image and the translation of the x in the x direction and y direction. Suppose if x direction you are giving translation of -100, means it will leave the boundary and the image will go in the left side of the original place. And similarly, if you are giving it +100, means in the y dimension, means it will get shifted to the bottom from the top of the image. In this manner, our translation can work. So let's run this code, and then we will see that what is going on. So this is our original image, and this is our translated image. So what is going on? Both in the bottom and both to the left side, both in the bottom as well as left side, your image got translated. So only that part is visible, and rest of the part is appended by the intensity 0. And the intensity 0 means the black in color. Okay, so this is the one way of translation. Then same thing means we can do rotation also. I am not commenting this code, because I have to import these things and read the image again otherwise. So what we can do, we can comment this part, just translation part, and I am keeping this part live, and then I am taking this rotation. And so what we can do here, here again this same ref affine keyword we have used here, but in the different manner. Here because we are using it as a rotational, then how much, what angle you have to rotate, that you have to give, and along with the dimensions. And so what is the thing here? This function we have created, the rotation point we have identified. That rotation point is just the width and the half of the width and height that we have taken, and then we have shifted. this complete just now we have created this function, rotate function, and we are creating this, we are using this function here to simplify our things, because when we give your code to some other fellow, it will be more user friendly if you can simplify the existing functions. Like existing function was the wrap affine, but here in this particular function you have to give multiple parameters to be specific as per the demand. But if you are knowing that your client or your user is already comfortable with some fixed things, and he should only input only one parameter, which is the angle parameter. So you can simplify your code for others, so the deployment and the transferring of the codes will be easy, and it can be reusable by the multiple users. That is one more way of coding. You people are better aware of this thing. So the thing is that if now the rotated image we have taken, and then we are trying to show it. So let's run the code and then we will see. So what will happen, this is our original image, and now we have rotated it, and the rotation angle is given, which is 45 degrees. And if you will change this angle, the corresponding things will get changed. That is already, that is understood actually. But still we can see. So what will happen here, this is the original image, this is your rotated image. So the rotation angle has been little changed. Now it is 60-degree rotation. So that kind of affine transform, actually that affine transforms are very much important. So in this feature extraction and feature augmentation and all, people usually use them. So that's why it is important. This is one more thing. So we are just commenting it part, this part also, and now we are going to the flip. So in flipping, if you will see, we are just trying to flip the image. That wait key, it is not essential, but in the advanced IDs. But if you are using conventional programming, better you should take care of this. So what will happen here? The inversion, the flip has been happened. Flip of this image has been happened, and you can flip your image. So this is the original image, and this is the flipped image. So that's why this flip is important. The horizontal or vertical, both kind of flips are also possible. That you can change. You can see its help, cv underscore, just type cv underscore help, help and help bracket cv dot flip. You can see that what other things it can do. So that is okay. And now we are coming to the next part, that is our contour detection. In one manner you can say the edge detection. So it is also, although already we have seen with the Kenny operator, but again, if you would like to see this, they're just dedicated for the contour. So again, we are taking the image, we are taking its corresponding grayscale image, because whenever this edge detection, gradient detection, texture detection, these tasks, whenever we have to perform, mostly we convert our color image into the grayscale image. So that we are doing here. And suppose if we are working on this Kenny, and that Kenny edges we are so again here we are trying to show the three images: original image, grayscale image, and the corresponding this edges. Only edges will be shown. So again, if I will run this, the three images will appear, and then you can see this is your original image, this is your corresponding grayscale image, and this is this is what has been done by the Kenny edge detector. You can change its parameters also, and then you can see the other things will also be okay. But so the main part of this Kenny edge detector is just to identify the contours. So in machine vision application and feature engineering also, many of the times the contours are sufficient to identify the things. So that's why it is important that we should know. And after that, this is the one part. We are just going to the next part also. Now we are looking to various color spaces, as I have already told you: RGB to grayscale, RGB to HSB, and then RGB to lab color space. So a lot of things are there. One by one we will show. We will see that how we can change from one domain to another. Why it is important? Because sometimes we have to process only one particular channel to treat the complete image. So when we work in the RGB to HSV conversion, when we do hue, saturation, and V for intensity. So that hue, actually V is for value, but that value is intensity value. So that hue, saturation, and V, HSV usually we say. So when we convert our HSV image to the convert our RGB image to the HSV image, we can only operate over V channel, and we can get our things done, because other things are just for imparting the colors. H and the hue and saturation model. Usually whenever we do the image restoration or edge detection things when we have to do, or segmentation things we have to do, then these things will be helpful. Along with that, one more thing is that, okay, we will try to show it. Just this first one is very much trivial. It is just to show its corresponding grayscale image by using, although we have seen this particular thing in multiple ways, but if you have to use this CVT color, because this CVT color command is only the command which is you doing the magic here. So better to focus on that. So that is one part. Now we are coming to the RGB to HSV. Again, we will use this CVT color only, but the how we are using that we have to see. Now HSV we have converted into the if you will see the originally in this OpenCV, we will have the BGR format. So the BGR originally from the BGR to HSV format we have changed, and we are trying to see it. So if you would like to see, then it will look like this. Like this is the same image, but this is in two different by using two different color models, or two different you can say the color schemes. Sometimes because this HSV is highly related how human perceives the color, and similarly for the lab color space and other color spaces are dedicated for the machine vision applications. So it is just domain dependent or application dependent, but we should know that how we can convert from one domain to another. That is the core intention of this part of the code. Now we can do the same thing for the color lab space also. Again, again only thing that we are changing is the CVT color. We are changing this parameter like color underscore BGR to lab. Similarly, it was color underscore BGR to HSV in the previous case. So if we will run this again, we will get this kind of vision. So usually this from this domain to this domain you can see. And now the point is that suppose we have to process only one particular dedicated channel, how we can do that? So for that we have to split the things, and before splitting we can see that how we can use this matplotlib library also to understand and to show it, because matplotlib those who have already worked in the image processing using MATLAB, for those people this matplotlib library is very much helpful, because all the commands are almost very much similar. Along with that, the graphical visualization or using this matplotlib.pyplot is very nice to understand the further things. So it is always advisable that for plotting purpose, if you will use matplotlib.pyplot, it is better. But we have to be careful a little bit. Like in the MATLAB, the sequence of the color formatting is RGB. Like similarly in the matplotlib also. But in OpenCV, when we work in OpenCV, it will be in the format of the BGR. Like blue first comes, and then green, and then red. And the color inversion is there actually. So what will be the effect of color inversion that we will show in this part of the code? That is very much essential. Those who are doing the cross-domain, cross-platform coding, for them it is required. So what is the thing here? First, we are reading the image. We are just showing the image. Now only difference is that in line number 251, we are showing this image using the IM show of the CV, means the OpenCV library we have used. But in the line number 252, we have used the matplotlib library to show this image. So what is the difference actually? The RGB got inverted. We have not done any processing here. If you are carefully able to see this, we have not done any processing here, but still our images color got inverted. Means the R become blue, the red becomes blue. Like our sequence was RGB in MATLAB, and in Python it is BGR. Okay, so G remains G, but the blue and red becomes inverted. Because of that, what will happen if this blue and red they both get inverted, then we will get this kind of image. So this is essential that if you are working in the CV2 and you are showing your outputs in MATLAB, the iPlots and all, then you have to invert those colors before transferring. Otherwise, things will become different. If you are working on the vision-based application, means the color-based applications. If you are working on the intensity-based, then the things will not affect much. But the color vision, color levels will get changed. Okay, so we have to take care. That's why if you are not aware of this or not want to get in trouble in these PyPlot. Although this PyPlot is very nice to understand, very nice to save the images, very nice to interpret your plots, unlike the CV2, like you can say the multiple facilities are also available in this plot, and here nothing is there in CV2. But here the risk of the color conversion is there, color inversion is there. So that color inversion we have to tackle anyhow, otherwise you can lead to the error. So that we have to see. So how we can do that? We can invert the colors, and we can before showing it. So that we will see in this part of the code. If it is visible, just let me run. Yeah. So what is going on here? It is the original case. But here in the what we are doing, we are again converting it to the BGR to RGB. Here PyPlot we have not used. Just to show, this code is just to show you that what was happening in the earlier code. Here we have not used PyPlot library, but only this BGR to RGB conversion we have done. Okay, so that means this is just trying to prove our observation that if we have converted from BGR to RGB, means already we have done the color conversion. And if we have done the color inversion, sorry, I am not, means it is not color conversion, it is color inversion actually, because the R and B got inverted to each other like that. So that was the thing that you have to take care if you will do the cross domain things or cross libraries things. Now we will jump to the merging and splitting and merging of these color channels. So what we can do, because if suppose we have converted our RGB image to the HSV image, suppose, and we would like to operate for some restoration or some other thing, then V channel is only sufficient. Means hue and saturation channel we can keep safe, and at the last when we have obtained our we will obtain our restored image, we will merge our hue and saturation components to that image. Usually we do like that in the enhancement, in denoising, multiple applications are there. So what we can do here, first of all, we are reading an image, we are showing that image, then we are using the split. When we use this cv.split, it is very much useful. Then your channels, whatsoever channels are present, whether it is RGB, whether it is BGR, whether it is HSV, they comes in this particular sequence. Okay, sequence is important. Again, I am repeating because in our in those who have conventionally worked with the MATLAB, for them it is like RGB. Like here, it is not RGB, it is BGR. Just please take care. And then we are trying to show all three channels one by one, and then we are also printing their shapes also. So obviously we know that the print means we will get our outputs printed in the console window, and other image show that whatsoever we will do, that will come as a pop-up on the pop-up figure. Now after this we are merging. We are here two commands we are using. One is this cv.split that we can use, and those who have worked in the MATLAB, they know the cat command was there, but instead of the cat command, here cv.merge command is there. So the cv.merge you can use, then you can use the square brackets, and you can keep your things in this order. If you will change the order, the things will become changed. That's why I have written one more line and commented it, that we will see once we will run this code. So if I will run this code, then you will see this is your original image. Then these are the blue channel, this is the green channel, there is the blue channel, red channel, and green channel. Okay, they all are looking as a grayscale, but when they are equivalent diagram, equivalent composition will get formed. That is the intensity variation in the blue, that is the intensity variation in the red, that is the intensity variation in green. And after merging all of this, we can obtain our original image, and you can compare. It is the same image which we have started. Okay, I think I have crossed it out. Now we will see. I think by this time you are knowing that the input image and the merged image, it is same. Suppose if we will change this code, means like if we will, I am commenting this line and I am uncommenting this line. What will happen? Obviously, I have given it in the wrong order, because the order of this OpenCV is not RGB, it is BGR. So now again the color inversion will be visible, like if you can see now. So what is this? Actually, I am okay now. Yeah. So this is your original image. Then these are the corresponding three channels. After that, the merged image is again we are getting the color inverted image. The reason is that we have not followed the convention of this OpenCV. because OpenCV work in the BGR format. So whenever you are merging, then BGR, if you have taken the blue as the blue as the B, G as the green and red like this, then again here we have to follow the BGR. So better to keep it commented, and we have to uncomment it. So here, if you will follow the BGR, your color inversion will be not there. Just we have to take care, because those who have worked in MATLAB, they can get the error at this particular point. And now we can switch to the next section. Just a very basic thing I have taken, like quality enhancement of the image, like visibility enhancement, you can also say, that is using the histogram equalization. So in this command, we will deal with the histogram also, that how, because till now we have not seen that how the histogram of the image works. So that is also important. Means pixel wise, means if you will say the intensity wise, their frequency, if we will keep it on the record and we will plot it, then we will get a 2D plot, and that 2D plot is actually histogram. Maybe the definition of histogram is clear to most of you. So here again we are using the 3 libraries: CV2 library, NumPy library, Matplotlib library. Then we are creating our own functions, dummy function, the user-based functions. You can, if you are not good enough, you can directly use their own functions. You can give the proper inputs to the inputs for the parameters of these standard CV2 functions. The CV2 libraries functions, it is equalize hist function is there. Here, if you are noticing, I have not imported it as import CV2 as CV, that I was doing in previous all cases. So this is just to show you the change, and that how, what is its meaning. If you are just importing the library, you have to follow its complete name everywhere. That is required. So here, every time I am writing CV2.cvt color, unlike the previous case when I was writing the CV underscore, I was skipping 2. So it is just to show you that you have to be careful, that otherwise it will show the error. So this is how we can do the histogram equalization. Directly command is there here. Actually, histogram equalization, for those people who are not knowing it, there is a probability distribution once we plot it for all intensity levels, and if we will make that probability distribution uniform, then the corresponding image will be called as the histogram equalized image. So the distribution of the intensity levels become uniform, and that's why sometimes, not all times, the visual appearance of the image becomes very nice. Mostly it happens for the very dark or very light images, mostly. Okay, that we can see. Now how we can visualize the histogram also, we can plot it, how we can plot and down. For this plotting, we are using this PLT, means like Matplotlib library we are using. Then we are showing the image, then we are showing the equalized image. This function histogram underscore equalization we ourselves have created. That was the original function which we have used. Then our a few parameters we have given. Actually, nothing new we have given. We have just taken that we have converted our color image to the grayscale image before taking the histogram equalization. That is the only thing we have done here. And again, the reverse thing we have not completed, like we are not showing in the color format. Again, along with this histogram equalization, I would like to show you that how we can darken our images, like how we can darken or how we can make it lighter, like the biased images. So for that, this dark factor we can use an np.clip. That np.clip is a NumPy libraries command. So what it do, it changes the maxima and minima of your array. So what will happen if your previous array was existing from 0 to 1, now the array get redistributed and the values will get mapped to the 0.3 to 0.7 also. So what will happen, in one way the range becomes less, and vice versa is also possible. So that's why this np.clip command we have used to make it little darker. And after that, what I am doing, I am trying to enhance this darker image using the histogram equalization. And then there are two ways to plot it. Like first we are plotting using the CV2. So what we are doing, we are creating first of all we are creating a stack. Then that stack is having 3 images. That horizontal stack we are taking, that is again a function, that is again a command from NumPy library. So that, because this is again an array command. So what we are doing, we are having 3 images: original gray image, then dark gray image, then its equalized image. And then we are trying to show all of them. We are trying to visualize all of them. Let's see what will happen if we will run this code. So if you can see, or we have plotted in both manner. We have plotted this result also. If you will see here, this first we have plotted this, then we have plotted their gray and equalized and other windows also. That's why these two windows are also coming, and along with that we have plotted the histogram also. That visualize histogram is the function which we have created, and that in this visualize histogram there is a plotting of this, which we are using the stem plots. So now we will see one by one everything. This is your original image in grayscale. Then this is your equalized image in the grayscale. I have crossed it out because already we are having these in this. So in this we have stacked. We have horizontally stacked all three images. So first image, this is the original image. Then we have darkened it. Then we have used the histogram equalization to enhance it. Although you are, although it is perfectly visible that as compared to the original image, this histogram equalization is not working that much proper. But if suppose you are not having the original image and your image is comparatively darker or not enhanced, you have to restore it anyhow. So then in that case, histogram equalization will be helpful. Okay, that is the one thing. Second thing is that this is our histogram, how we can show it, how we can see it, how we can understand it. Actually, here I have plotted only one histogram, like input or output both not plotted. So we can see that here there are multiple levels starting from 0 to 255. Then how many pixels, here frequency is written. Frequency means how many times that particular intensity is repeating. That is the number of pixels those are containing that particular intensity. Those are having that particular intensity. So that is your histogram. If you are not knowing what is histogram. And also one more thing, that histogram just now I have crossed it out. So that was not uniformly distributed. But if you will make it previously it was not uniformly distributed, and if you make it uniform distributed, then you will get the histogram equalized image. So again, I am putting this part on the hold and keeping it in the command form, and then this also we have seen. So yeah, up to here. Now we are just leading to the last part of this. Like one more example I have kept for the image denoising, how we can deal with it also. So here what we have done, we have taken the image, we have imported these libraries, read the image. We have added intentionally some noise in this, and this is not very good denoising technique, but just I am saying that one non-local mean denoising technique, it is inbuilt in this CV2. Like this, various other denoising techniques are also are also implemented, and or also their dedicated keywords are defined in OpenCV library. Just corresponding parameters you have to give, like what is the size of the window size, what is the size of the regularization factor and all. So once you do this, then you can use this single command for denoising the image, depending upon the behavior of the image and depending upon the behavior of the noise also. Okay, so here again we are creating an horizontal stack, means we are taking the gray image, we are taking the noisy image, we are taking the denoisy image, denoised image. Here the effects are not much visible, but we can see that what is going on. So once we run this code, then you can see this is our original grayscale image. We have added some noise intentionally. Then we have done the denoising here. But here in this denoising, if you are observing that some noise component has been reduced, along with that, some smoothing also has been happened, which is a byproduct of usual denoising. Whenever we denoise, but actually noise is the high frequency component. So whenever we add the high frequency component, the image becomes noisy, and when we have to remove that high frequency component, we have to denoise it. Usually we do the smoothing or low pass filtering. So means in one way, because we are doing smoothing where the error is not high, so that part will get more smoothed. So that's why the smoothing is a byproduct of this. And sometimes while doing the denoising, blurring is obviously as a byproduct. So we have to define our methods in that manner that that smoothing should not be more, and the denoising should be more efficient. So just by looking, just again, if you would like to revisit this code, this line number 353, we are creating a artificial noise, synthetic noise. Then in line number 54, we are adding the noise to our original image. Okay, and after this we are trying to denoise it using this line number 356. In this way this code is working. The other things are just to create, just to take the inputs and create and take the outputs, that's all. So that much is sufficient in this denoising. Means you can explore yourself for further methods, and first go through all the existing methods of denoising or some dedicated programming in this available in the CV2. Then you can modify those existing codes according to the demand that we can see. Similarly, I have taken one example of image segmentation, like it is the clustering based segmentation. So suppose usually as we have seen that image is any image is composed of 256 intensity levels, but why not we can see those images if only some particular dedicated task of object detection or that kind of thing you have to perform, then why not we can have to represent in less number of levels, because if we are able to represent that image in less number of intensity levels instead of 255, if we are able to identify that image things in 2, 3, 5 levels, then it will be more efficient when we work with the machine vision or computer vision applications, because our machine has to tackle only 3 or 4 intensity levels. That's why segmentation is important. So here again we are reading the image, we are importing the libraries. First of all, that's why I am importing the libraries every time, although I could do it only once, but just to show you what is the complete gist of the code, and complete tagged code you should write, that will be better to understanding. And the image first we are reading, then we are creating a we are just making its reshape and just to create it into the one vector format. Then we are applying the k-means clustering. For applying this k-means clustering, this CV2 underscore k-means direct command is there. Just you have to parsing its inputs and corresponding parameters you have to take care, and you have to give the corresponding things. And so inputs if you will give it will convert it into the k-means. Like what will happen if we have given this k is equals to 3, means entire 255 intensity levels will get mapped to the 3 intensity levels, means they will get grouped they will get clustered into the 3 intensity levels. So we will see that what kind of outputs we are getting, and correspondingly we will also see that what will happen if we will increase or decrease this k value. Obviously if we will increase, the image will become more clear, but the more computational complexity, more levels our machine or computer has to see. So that's why it is always advisable, if for segmentation, if less number of levels are sufficient, then we should go for the less number of levels. Okay, so this is one more code, one last code we are running. So it is the thing which is visible to you. This is the original image, and this is the segmented image. Here only 3 intensity values we have used, and I think you should observe that this number is also visible even only if you have used in 3 intensity levels. Also if somehow it is also visible that what is in the image. Here we are able to count those number of objects also. Suppose the cat is our object under consideration. This number of cats are 4. These 4 cats are also able to be counted if we are using only 3 regions. So if we will increase this k is equals to 3 value to the 10 suppose, then also you will find the segmented image which is having 10 clusters or 10 regions. But sometimes it is useful depending upon the application. But if you see, and again one more thing to observe here is that using 255 levels you are getting this image, and using only 10 intensity levels you are getting somehow very clear to understand image. Means if your objective is just to count the number of cats, or if your objective is just to identify whether it is a cat or dog or some other animal, or if your objective is just to identify the number of this basket which is written there, then I think sometimes 3 to 10 any means more than 3 or just equal to and more than 3 any intensity levels are sufficient. But obviously as per our segmentation understanding, less number of levels, if they are able to do the same thing, it will be more helpful. Okay, so that was the purpose of this complete talk, just to give you a glimpse so that further things you yourself can explore, and you will have a little bit foundation. If although nowadays I am expecting that most of you are already familiar with all of these things, but still I have included that. So thanks for your patience. If you were already knowing all these things, and if you are having any queries, you can mail me also, and you can right now also you can ask me. And along with that, I will share all these slides as well. Although nothing much in the slide, but still I will share slides as well as the code with the coordinator, and then coordinator can circulate this with you. Anything if you would like to discuss, you can ask, please. Okay, Dr. Santosh. Okay, if no further queries, then yeah, thank you everyone for your understanding and for your patience, for your listening. And if any further queries are there, then again you can redirect your questions to me. I'm working as an assistant professor in Amrita. I am so you can go through my webpage also, and you can you can come in contact with me. If anything, if any new thing is not there, then we can conclude this session. Dr. Santosh, are you there? Okay. Along with that, I will share all this stuff with the coordinators. I am repeating. Thank you from my side.
Thank you, Himanshu sir. It's a wonderful session, very informative. Yeah, yeah, you share your PPT and documents. We will circulate to the participant.
Okay. Thank you.
Yeah. Thank you so much, sir.
Thank you. Thank you, everyone.
Thank you.
And leave it.